So, plus to minus, but no change in handedness. Plus to minus, but no change in handedness. Complete? But now again, how is this plus taken to this minus? Mirror will change handedness. Handedness has not changed. It can't be a mirror. One more twofold. You require another twofold. If this was along x-axis, you need a twofold along y-axis. You need a twofold along y-axis. So again a Swayambhu twofold. Without adding any new points. I only am adding a twofold, new twofold, because points are already there. If I added this twofold, what will it do? It will take this plus to that minus. I have already drawn that. Okay. Look at this. This is a glass one, I should not sit on that. Look at what is happening. I take this plus to this minus by this twofold. I had that. I had that in my toolkit. I took this plus to that plus. I had this twofold. I had it in the toolkit. But then I have to take, for completeness, I have to take that plus to that minus again by this twofold. So I went there, the left one. But now the group theory requires that this plus should be taken to that minus also by some symmetry operation. That is not this twofold, that is not that twofold, so it is something else, and that has to be part of the group. So that is this twofold, new twofold. So for twofold also, n-fold axis will have, so twofold perpendicular to n implies n twofolds perpendicular to n. N twofold perpendicular to n. Okay. Apply the same philosophy to other ones. So what will be the point group called? 2, 2, 2. Which crystal system? 3 twofolds, orthorhombic. So 2, 2, 2, orthorhombic. I apply it to 3, 3, 2. Although, so this, it's not that here there were 3 twofolds, I wrote 3 twos. Here also there are 3 twofolds, 3 horizontal twofolds. But in the symbol wise I am writing only 1. You are supposed to understand from this 3 that there will actually be 3 twofolds. So the point group symbol is only 3 and 2, 3, 2. Which system? Trigonal. 4, 2, 2. System? Tetragonal. 6, 2, 2. Hexagonal. Whenever you are trying to feel bored, depressed, it's appearing that life is meaningless, start with a circle, draw a 6-fold in the center, draw 6, 2, 2, you will feel very happy and the depression will go away. 6, 2, 2. So that's why I am not doing it. That is a medicine left for you. So we have now combined a rotation axis with a perpendicular mirror. We have combined a rotation axis with a parallel mirror. We have combined a rotation axis with a perpendicular twofold. How many point groups we generated? Let us count. 1, 2, 3, 4 and 6. 1 bar, 2 bar, 3 bar, 4 bar and 6 bar. And 2 by m, 4 by m, 6 by m. 3 by m not there because it is 6 bar. Then we have mm2, 3m, 4 mm, 6 mm. Then I have 222, 32, 422, 622. Good progress. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 point groups out of 32. 2/3 of the work done. 2/3 of the work done. Let us now draw some of the other point groups. Let me draw. Let me now not trouble you so much. You have now got the hang. That is the whole idea. Not to spend entire time drawing. And if you Google, if you click Wikipedia or something or some other book, you will find the table of 32. And in previous earlier days, when I used to take class, I used to bring a nice chart to distribute, just like this time I distributed empty circles. I used to distribute filled circles, but I thought it is not a nice thing to just give the filled circle, because students are bright, they can fill the circle on their own. That's why this time I have given you empty circles to fill on your own. So other point groups can be worked out. Let me just try to now the cubic point group. Okay, cubic point group, very, very, very interesting, because very complicated. So let me draw a cube. इतना ही ड्रॉ करते हैं. What all cube has got? Let me first draw the mirror planes of the cube. It has got a horizontal mirror plane. Okay? You all agree? That's a mirror plane. So my stereogram should also have a horizontal mirror plane. It has this vertical mirror plane. So my stereogram should have a diagonal representing the vertical mirror plane. You are following? You are with me? Cubic stereogram, one of the most beautiful objects ever created in the world. You will see how beautiful it looks. Then another mirror, so another diagonal. This is also vertical plane, and this is a vertical plane which is at 90 degree to this vertical plane. So this is a diameter which is 90 degree to that diameter. Okay. So I have the x plane, y plane, the 3 coordinate planes. The 3 coordinate planes are now represented here as mirror planes of the cube, the x plane, y plane, and the z plane. I have another vertical mirror like this, which is at 45 degree to these other 2 mirrors. Draw that 45 degree diagonal. I have another vertical mirror again at 45 degree, but oriented differently. अच्छा लग रहा है ना? Surprisingly, all I have drawn now how many mirrors? 3, 4, 5. Cube actually has 9 mirrors. 4 more mirrors are left. Let me try to add those 4 more mirrors. Where are those 4 mirrors? Let me change the color just for better identification. there is a mirror like this. Isn't this a mirror? Slicing the cube like this. This mirror will be a plane which will now not be, since it is an inclined, it is not a horizontal plane, so it is not the circle. It is not a vertical plane, so it is not a diameter. So, it is some another circle for which you have to now understand the details of stereographic projection, which I hid under the carpet, and which I will keep it hidden in this class. You have to go and study more detailed stereographic projection to see that how this 45-degree inclined mirror plane is represented by this line. So, 45-degree mirror plane. Another 45-degree mirror plane on the other side. This is also a mirror plane. So, next time, how many of you like making rangoli? Nobody. Nobody makes rangoli nowadays. कोई तो बनाता होगा, नहीं बनाता है तो बनाओ. And I am providing you a design for rangoli. वर्कशॉप से क्या सीख के आए? रंगोली सीख के आए. This mirror, and finally, I have run out of color. Finally, this mirror. This mirror. इतना सुंदर रंगोली कभी नहीं बनाया हो. अभी रंगोली कंप्लीट नहीं हुआ है. We have just added the 9 mirrors of the cube. We have just added the 9 mirrors of the cube. What about the rotation axes? You said that there is a vertical fourfold perpendicular to the face of the cube. लगाओ. But perpendicular to this face also is a fourfold. But that is a horizontal twofold. That is a horizontal fourfold. So it will come on the primitive. It will come on the primitive. Right? I can draw it in 2 minutes. I am taking time to engage you and engage your imagination and thinking, because then only you will appreciate that what has been drawn. So, a vertical twofold in the center, horizontal twofold on the circumference, another horizontal twofold. कौन बोला? सत्य. Thank you for correcting. Who says that it is twofold? So fourfold. I was only checking whether you people are alert or not. There is an advantage of being teacher. Okay. Never accept any mistake. Whatever mistake, I was checking whether you are sleeping or not. And if somebody asks a question and you don't know the answer, teachers in the group, if somebody asks a question and you don't know the answer, what will be your answer? What will be your answer? The teacher should respond. A student has asked a question which you don't know the answer. What will be your response? Yeah? तुम्हें पता लगे तो मुझे भी बतलाना. No. That's not a good teacher. Good teacher should answer such a simple thing you don't know. What have you been doing all this time? It's a class 10 physics. How did you get in up to this place? Yeah. So I have done. So cube has 3 4 folds. 3 4 folds. One vertical, second horizontal, third horizontal. 4 folds done. Cube has 3 folds in the body diagonal. Where are the body diagonal? Here is the body diagonal. Look at where is it located in the real space. On the orange mirror, on the red mirror, and on the blue mirror. Where is the orange, red, and blue mirror intersecting? There is a 3-fold. And really, now a secret, really the 3-fold of the cube is not 3-fold, but 3 bar, 3-fold roto inversion, because cube has an inversion center also. So on the 3-fold, an inversion center is lying. If a 3-fold inversion center is lying, it becomes a 3 bar. So it's not really just seedha 3 axis. Oh, come back, yeah. So international notation. Was I able to draw? Let me first fill it and then try to draw. Fill and then select. I can select white. So I make a hole. Yeah. This looks better. Bindi. A triangle with a bindi. 3-fold with an inversion center. 3 bar. So 4 3-fold, 1. I told you how to find it, so now you know how to find it. Four 3 bar. See how the rangoli is coming? Are all the symmetry operations have been drawn? What is left? 2-fold. Where is the 2-fold? Middle of the edge connected with the opposite edge. Middle of the edge connected with opposite edge. And it's lying on the mirror. If a 2-fold lies on a mirror, how many mirrors should be there? 1 and 2, 2 orthogonal mirrors. Just find wherever 2 mirrors are intersecting, fatafat put 2-fold. 1 2-fold, 2 2-fold, 3 2-fold, 4 2-fold, 5 two-fold, 5 two-fold, 6 two-fold, 6 two-fold. Have I completed it? Are there only 6 two-fold? Pair of opposite edges, centers of pair of opposite edges is defining a two-fold. Cube has how many edges? 12. So how many 6 folds? 6. So I have drawn 6. 1, 2, 3, 4 inside and 2 outside. M 3 bar, M that is the M 3 bar M Rangoli. The final. So, say this is the most symmetric point group. 48 when you will count 48 symmetry operations, order of the group 48, highest number in the entire 32 point groups. So, since this is the final one we have done, point groups is done. Cubic, look at the cubic row. Look at the cubic row. There are 5 cubic point groups. So, this is the complete cubic symmetry, and the cubic symmetry, the notation is the first M should be 1 0 0. That is normal to the 3 axes. So, I should not write, or since I need all 3 axes, the bracket should not be square but angular. 3 bar is along the body diagonal, and the last M is along the face diagonal. So, that is the notation of the cubic symmetry group. This is the notation of the cubic symmetry group. M 3 bar M, holohedral. So, next time you make a Rangoli, make sure that you make M 3 bar M Rangoli. Any question? So, the point group is done. We have 32 point groups. We have 5 monoaxial point group 1, 2, 3, 4 and 6, and another 5 monoaxial roto inversion groups 1 bar, 2 bar, 3 bar, 4 bar and 6 bar, and we have various combinations of these, some of which we have seen, 21 of which we have seen, 10 is left for some future workshop, or come to Delhi and I will explain to you. So, now since it was promised, let us see how much we can do of the space group. Yeah. No, tell me, I will go back. Okay, screen was not coming. Yeah. Yeah. My email and my phone number for anyone to contact me in future. Sir, I will recommend you a specific medicine for a specific problem. Okay. Sir, I am having headache. Draw 4 bar 2M. Sir, I am having huge depression. Draw M 3 bar M. So, online consultancy will be given at these numbers free of cost. Yeah, this we have done. Yeah. Now the space group. Now that book is just like 32 point groups, 230 space groups. Now translations are being combined. So strange things are happening when you start combining it with translations. And the number grows from 32 to 230. And all those 230 symmetries, not easy to draw. I drew 21 in one day. 230 I may not be able to draw. I have never drawn in my life. And I don't know whether after Kathleen Lonsdale, anybody else tried to draw it. So, all of them. So, in the space group, I should have somewhere, do I have international table? Yeah. Yeah. International table for crystallography, the current edition, editor Arroyo, 6th edition, editor Arroyo, who, if I am fortunate, I will see in Rourkela, end of February. Means it's a workshop like this. A workshop where anybody can register and come. So I don't know whether you are knowing or whether you are interested. So Arroyo is coming there. So huge book. Huge book. I showed you. Yeah, राउरकेला, झारसुगुड़ा. राउरकेला का कौन है? राउरकेला से कोई आया ही नहीं. They don't need it. They are getting Arroyo to teach. Why they will learn from Rajesh Prasad? Yeah, no, I was showing the last page just to see the count of the pages. 873. 873 pages of symmetry and symmetry and symmetry. 230 different space group. Lot of, apart from symmetry, there is discussion of symmetry. Lot of articles are there. You should read. See how nice. How nice articles are there. Let me show you. I am not able to move easily. I don't know what is happening. Yeah. Some of the point groups which we drew was, I think, visible. चलते चलो. Yeah. So this is the kind of symmetry. So 222. Remember 222 point group? Orthorhombic. Now you see the meaning. P is primitive. P is primitive. And 222 is the point group, so it's orthorhombic. And how is the symmetry distributed? So it will only have two folds. So the two folds are shown. This is now in the space group the notation a little bit changes because you don't draw it on a circle. So you draw it in a unit cell, rectangular unit cell. So this is now the vertical two-fold perpendicular to the plane of the page, and the two folds lying in the plane of the page is shown by arrow. So there is a two-fold going this way, there is a two-fold going this way, two horizontal two-folds and a vertical two-fold passing at this point. But now since it is a space group, translations act on it. So this is the edge of the unit cell. So another similar point goes there, here and here. And then there are other two folds get generated. So they are shown. So the space group. So the top part, there is a lot of information. And I think we will end with that, I think. Beyond that, it will be difficult to go. So the top part, just these two lines. These two lines have a lot of information about the space group itself. So that is called the headline. So let us look at what are the contents of the headline. That is what I was going to do. Yeah, headline. So so that kind of pages are there. I only showed headline. Why not show the whole page? Yeah. So there is the headline. Then there is a symmetry element diagram. Then there is some origin asymmetric unit, symmetry operations. Then there are this so-called Wyckoff positions, multiplicity, Wyckoff letter, site symmetry, Wyckoff positions. And then there are symmetry operations, symmetry operations. So all these things are there on a page, and one should be able to understand. If one understands all these things, one has understood a space group. So let us make an attempt. A long journey always begins with the first step. So we will begin with the headline. So I have taken group number. So all these groups by Kathleen Lonsdale. I'm giving all the credit to Kathleen Lonsdale, but of course actually there were two editors. So there was another, I think Henry or someone, two editors were there. So they numbered all the 230 space group starting from 1 to 230. So every space group has a number. So now this is also an international number. This is an international number, in the sense that if somebody says space group number 3, it can't be any arbitrary. It has to be space group P2. Okay. Now yesterday, I think the cubic drawing the cubic symmetry was hard work. So I am feeling warm. Yeah. So let us look at the headline of space group number 3. So a number is given. So it's easy to search. Then there is a name. So just like the point group names I shared with you, M3 bar M for complete cubic point group symmetry. Similarly, space groups also have a name. So this is P2. This space group is called capital P2. Number 3. Space groups were developed by two people, Schoenflies and who was it, Russian? Fedorov. Fedorov in Russia and Schoenflies in Germany. So Schoenflies developed a naming system. So his naming system is also included. So this is the Schoenflies. So let us write. You can write also in the boxes provided. So P2 or I should write this as short Hermann Mauguin symbol. Short Hermann Mauguin symbol of the space group P2, and this is Schoenflies symbol. This is space group number. And this one, every space group has a short HM symbol and has a full HM symbol. So, this is a full HM symbol, HM Hermann-Morgan. So, full HM symbol. To the point group, if you forget the translation, the space group will have point group, and the translations are encoded in this primitive. What are the translations? Only along the edges of the unit cell, no body centering, no face centering. So, P represents the translations. Cut out the translation, what remains is the point group. That is why 2 is the point group. And now you have sufficient gyan to say that a point group having only a single two-fold will be belonging to which crystal system? Monoclinic. So, this is crystal system. Patterson symmetry छोड़ दो. Patterson symmetry. This is okay. Now, if you see, yeah, now you should not see, because Bharati ma'am has come to close the event. So, no, Bharati ma'am, let us take a better picture. Now take. Now take. See, they are laughing. Sure. थोड़ा हंस दो. Yeah. So, yeah, each crystal system has a particular style. At the most, after P or something, after the first letter, so the first capital letter centering of the conventional unit cell. अब conventional लिखने का जगह नहीं, तो cell लिख दे. Centering of the cell. So, P primitive. If it was face centered, there will be F. If it was body centered, there will be I. So, the first letter tells you what kind of unit cell it has, and the rest of the part gives you the point group operations. So, now Bravais lattice is not given. But now let us do it step by step. Somebody throws P2 at me. I do that to my students in the exam. So, I will give the symbol and ask all the other details, because everything is encoded in this. P2 is entire space group. P2 is entire space group. All information, M3 bar M is point group, but P M3 bar M, simple cubic, P M3 bar M is the entire space group. All information can be decoded. That's the power of international tables, and that's the power they have designed this Hermann-Morgan notation. Hermann-Morgan notation is designed such that everything rest of the, if you are intelligent enough and if you have understood it well, you don't need to look at whatever is there in the rest of the page. You just have to look at this corner. P2 समझ में आ गया what all is there. क्या समझ में आया? P primitive, okay. 2 point group 2. Point group 2 means crystal system monoclinic. crystal system monoclinic, centering P. So, Bravais lattice, primitive monoclinic. Just just 5 minutes. आप बंद कराने आए हो ना? अच्छा, तो बंद करते, जल्दी बंद करते हैं, जल्दी बंद करते हैं. So, Bravais lattice monoclinic P. Okay. This table I have created, that which crystal system has what point groups. That answer is already there in the other chart. You can simply copy from there, copy and paste. Okay. This, and here I am showing you what I told you. Space group P2 means point group 2 means crystal system monoclinic, and I have already told you how to find Bravais lattice. Space group P2, point group 2, crystal system monoclinic, Bravais lattice monoclinic P, MP. And I already gave you these symbols. Triclinic. What happened? I can't write. Triclinic A, monoclinic M, orthorhombic O, tetragonal T, trigonal H, hexagonal H, cubic C. Centering symbols you all know. You are just repeating what we have done yesterday. Review. Primitive. मंगवा लीजिए. कहाँ पर वो बाहर जाएंगे कि यहाँ पर होगा? बाहर. हाँ अंदर मंगाइए. अभी इतना जल्दी डिस्क्लोज मत कीजिए ना. Primitive, A centered, B centered, C centered, end centered, body centered, face centered, or rhombohedral centered. Rhombohedral centered. लावे क्लास भूल जाओ. पैटर्सन सिमेट्री भूल जाओ. हो गया, हो गया. ताली बजा दो. Any doubt if you have, you can ask. Let us do this last line, because if we have done the first line and the last line means everything is done. Okay. So, IA3 bar, what is the point group? I did not tell you something more was required, and for that some more time is required. So, we did not tell you that there are symbols like A and D. These are glide planes, and when you convert it into point group, the glide planes should become mirror planes. So, A is a glide plane, will be replaced by M. D is a glide plane, will be replaced by, A is an axial glide plane, D is a diamond glide plane. So, diamond, but a lot of details are there. So, 40 hours of NPTEL videos are available on description of all these things. Okay. I have an NPTEL course which has been recorded, and so if you search somewhere it will come. Yeah, on YouTube. on crystallography. It's named some horrible name I gave. At that time I didn't realize. So it's called crystal symmetry and tensors, but there is no tensor in that. It's only crystal and symmetry. So let us do this. So A and D are glide, not done in this workshop, but I am telling you now that they are mirror planes. So point group, get rid of I, change A to M, 3 bar remains 3 bar, change D to M. What is this point group? It's cubic. So this is space group, you know now that this is cubic. Crystal system, cubic. Bravais lattice, body centered cubic, cubic I. Patterns and symmetry तो पढ़ा ही नहीं. And yeah, there is a nice line. Yeah, there is a nice line. Best wishes for your crystallographic. Best wishes. Yeah. Any doubt or question if you have, you can tell. Till something interesting is coming, you should keep asking. Okay. But I am not able to see the birthday girl. She has disappeared.
Before that, let's thank Professor Rajesh Prasad for this really long interactive lectures, and I think that all of you enjoyed his talk. And he said that he has some of these things recorded on YouTube.
Photo.
कौन photo लेगा? Somebody has to take photo.
No, he is also taking it.
नहीं photo होना चाहिए.
Proper photo. Your photo I cannot wait for you to send.
So thank you.
Yeah.
And I think this is
Bharti ma'am आ जाइए.
I think this is just the beginning.
But more than this, I want that.
Yeah, we'll give you, sir.
We'll have that. And I think this is just the beginning with you. We will be bringing him to your institutions also. Just this time you saw him here. Now next time you will see him at wherever you are.
Kumaon University.
No, not only there, everywhere. Thanks. Thank you very much.
Yeah, thank you.
किसका birthday है भाई? किसका birthday है?
Morning I was informed that somebody's birthday is there.
Yesterday, tomorrow, day after tomorrow. Please come. We have 5 cakes.
Yeah, during this period.
We have 5 cakes. We have 5 birthdays.
Anybody during this period.
One on each day. Your birthday is tomorrow. Come.
And the
Nobody else? There is no bombs or anything.
this and speaker takes one. The rest can do.
The organizer takes one. Come. Anybody's birthday from Monday to Friday. This month.
Okay, this month. January birthdays.
January birthdays. No? Okay, then you have to cut all the 5
December
cakes.
birthday.
Please. It gives us a... Come.
Yeah. Your
Yeah, projector. You are from Kolhapur or you are from somewhere else? Sangli district. That near the City Science? It's far away? Ahmednagar. Where is in Ahmednagar?
अभी टेस्ट होगा this exam 4 mm symmetry
Oh, this is going to face it?
that will recall that we put the house on fire
Yeah. Immediately you do it.
but first you have to blow that out na? Cut a big piece for yourself.
You can take one full maybe.
Photo. One more. One more. Yeah.
I don't cut it over it.
Please take some please. Small or large depending on.
Back in this afternoon lecture. So again today we have two lectures. The first one will be given by Professor Mrinmay Mukhopadhyay. He is a professor at Saha Institute of Nuclear Physics in Kolkata, and he will talk about surface scattering techniques. And then at 4 o'clock we will have another talk by Professor Rajesh Prasad. He will continue, and then that will go till he really finishes his planned, his exit strategism, right? So you have to do something to, get an exit pass. So hopefully something will be there also. So, but let's start with the talk by Professor Majumdar on the surface scattering techniques. So, Professor Majumdar.
Entry is free, exit is charged.
Okay, guys. Okay, it's always difficult to give a talk after lunch because always we feel sleepy, and I am also feeling sleepy. I am not. I don't know whether this will work or not. Okay, that's fine. So, I am Mrinmay Mukhopadhyay from Saha Institute of Nuclear Physics, Kolkata, and what I will be talking about a technique that is useful for thin film characterization mainly. Okay. So, before that I should make the stage for this why thin film characterization is important and what is actually you need to know to have a idea about the thin films and other materials. So the topic is surface scattering. So there are several surface scattering techniques, and one of them is being used by many people with the X-rays. So this is the main topic, that out of those surface scattering techniques, X-rays as a tool for structural characterization. Okay. So now, each words are important here because X-ray I am going to talk, and for structural characterization. So I am not going to talk about the spectroscopic part of the X-ray. I am going to talk about the structural part. That means the previous talk you heard is from Sanjay. He was talking about diffraction and how you have a crystalline materials, and then how you can get the idea about the crystallinity, structure, and then lattice separation, lattice displacement and all and more. Okay. Now, okay, that's right. So, what the outline is basically some basics of structure surface characterization and then basics of X-ray scattering. So, why X-ray is important and how X-ray interacts with the material to have your scattering pattern. So, that is what I am going to talk about a little, and then there are two techniques. So, one is the X-ray reflectivity. So, this technique is very useful for thin film materials, and what we know that this is important to understand in a thin film. It is important to understand the thickness, the roughness and the material density. So, those all the technique, those all the parameters can be extracted from X-ray reflectivity, then how you do analysis and all, and then another technique which is grazing incidence, small angle scattering, but small angle I do not know why I wrote small angle scattering, it should be grazing incidence refraction. So, there is a misplacement. So, I will be talking about this part, and then there are two very good books for reflectivity and X-ray scattering and all these things. So, one book is this by Alf Nielsen, Elements of Modern X-ray Physics, and the second book is by Metin Tolan. So, you can, if you want, you can go through this book and you can get more idea. Okay. So, the basic thing of my lecture is that I will be talking little and you will understand something, I hope, and then you will go back and read those books or these review papers and other literatures, and then you have a better idea what you want to do, because the thin film characterization is very important in all engineering stream or the science stream in general. Okay. Let us start from these things, surface and interface of the material. Okay. So, why we need the surface? So, why we need to characterize the surface? Okay. So, now you know that surface to volume, surface area to volume ratio, it goes by 1 over r. So, 1 over r means if you just take a simple approximation that this is my spherical object, and then you can do, and this is goes as 1 over r. So, here I gave a table, this is also you can get in Google, no problem. So, because if you have a number of particles, you have a 1 centimeter cube of material and it is a 1 particle. So, basically you have a 1 particle, and that particle, it may be crystalline, amorphous, whatever it is. So, that has basically 1 centimeter cube, and then the total surface area basically 0.0006. Okay. So, millimeter square. So, and if you just keep on increasing the particle within this box, just you have basically you can separate it with several cubes, and then you fill it up with this cube, and when you reach something like 10 to the power 18, you are not yet there in 10 to the power 23, but you are something at in the range of 10 to the power 18, then your surface area is 600 meter square. So, that means that when you go for smaller and smaller particles, then the surface area is very important, and that surface area dictates the property of the material, because that is the, so there is a bulk property and there is a surface property, because surface is different, right. If you are talking about water, let us say water is a very good example. So, if I talk about water we know the bulk property, we have viscosity, surface tension and all these things, and this is like a, when you have a bulk material, bulk water, it flats, right. Because of surface tension it is flat. Now, surface tension and gravity it is flat. Now, if you just reduce the amount of water, start to reducing the amount of water, and then at some stage you will basically having some droplets, and then your droplets can be millimeter droplets, can be micrometer droplets, and can be nanometer droplets. But when you are in nanometer droplets, then can you really call it water? Because water, we generally know that it has hydrogen bonding, and because of that bonding it is basically a liquid, right. Without hydrogen bonding it is a gas. So, now if you have water which is a nanometer droplets, then do you really call it water? Well, that's the question. And then the property, all the property will change, and that is a big topic in research, that water research. If you start is searching in Google or whatever, you will see that water research is a big area, and everybody is trying to get the correlation and how this property will change as you go down and down and down, so in the scale of nanometer. Okay, so this is basically a glimpse of what I want to say, that the surface characterization is very important for your materials when you go for smaller particles. If you are in a bulk material, if you want to big, you don't care much, but you want to have a smaller particle, because the problem is that, okay, let's assume this thing, this polymer paint. This room has a lot of painting, right? So just by reducing this polymer paint thickness by few micron, you can actually have a very cost effective material, right? Because you change the thickness, you need less amount of material, and that will give you more price benefits. But then you have to think that if I go very thin layer, then it will duet with time. Duet means it will make a droplets. So how to make a polymer paint without duetting over a longer period and longer humidity or longer temperature stability. So this whole thing, that means that even polymer is a bulk material. If you go for a thinner paint, then its surface area is very important, and then the properties of those materials will be very important. And then you need some material, basically systems to some mechanism to characterize the materials. And then what is characterized using surface characterization? So surface may be characterized with respect to topology. That means how rough is this? So when I touch a surface like in this floor and touch a surface like this have a different topology, and we call it that it has a different roughness, right? And then chemical composition, surface orientation, thickness, and all these things important. So typically how we proceed? So we proceed that the mean free path of the probe into the sample is low, or the sample comprises only surface atoms. So basically when you want to probe the surface, then you need a system, need something that doesn't go into the bulk, that stays close to the surface and gives you scattering, because gives you the information. Because if you go into the bulk, then the problem is that bulk has enormous amount of molecules or atoms, right? And then when you go bulk, your signal is more predominantly dominated by the signals from your bulk atoms, not the surface. So you need a probe that basically doesn't go much deep into the material, and it is actually probing the surface of the system. So there are a couple of methods. So you can characterize it, you can basically segregate it in contact mode and non-contact mode, and then there are destructive mode and non-destructive. So what is contact? That means you are touching the surface, and non-contact means you are not touching the surface. And destructive means you are not destroying this material, you are determining the structure or the property of the material without destroying the structure of the material, and in some cases you have to destroy and know it. Okay, one thing is that there is no course like I have to complete this part. Okay, so whenever you feel, you just stop me and I will explain, or I will try to explain. That's all. So there are several non-contact surface characterization technique like X-ray and neutron. So these are some elementary particles. X-ray is not particle, but X-ray, if you say photons, those are quantums of this X-ray. X-ray and neutron reflectivity, you can do that. You can do X-ray photoelectron spectroscopy that I was talking about, that I will be not talking about this spectroscopy anymore here. And then there is a secondary mass trace. You saw that I have colored it differently, and that is because this is a destructive technique. So you actually erode the surface, and then by eroding this surface, you can uh, identify that what are the materials are there and how they are distributed, and also you can get a lot more information from these things. And then was the electron spectroscopy, electron diffraction, and then also electron microscopy. So you will say that X-ray, neutron and electron. So these are kind of three fundamental elements or particles that we will use for these scattering techniques. Okay. So if you go in transmission electron microscopy, TEM, any unit, you will see that there is a electron diffraction, and from electron diffraction you can calculate the lattice and easy, right? This is easy because this is a lab setup, and you can do that in just by placing the sample. But then the problem is that in transmission electron microscopy, you have to prepare your sample in a way that you can measure it. So you have to make it a very thin slice, or you have to cut it in a proper way that you can see all the surface atoms and all the materials along the space, and by cutting this thing you are expecting that you are not destroying the structure. But the advantage of X-ray and neutron is that it is the non-contact mode. So you do not need to touch the material, you just probe with X-ray or neutron, and then you have whatever you are getting like diffraction or some other, and then from that you can model the system and you can measure it. And scanning turning microscopy you will have a class on this, right? So this is the basically the electromagnetic spectrum. You can see that all the molecules are there, water molecules all the way to the soccer field, and also there are basically intensity and all these things. And here I wrote synchrotron, which I have a plan at the end that I will be talking about if time permits. Okay. So what are the elementary particles that can be used as a probe for this at this nanoscale? So one is neutron, X-ray, electron and ion. So these are fundamental, kind of not fundamental, ions are not fundamental, but these are kind of elementary particles that can be used as a probe to characterize the material and specifically the surface. Okay. Neutrons have the advantage. Neutrons, okay, I will start with the electrons. Okay. Electrons is easily available, very easily available, right? You can have a basically filament and you can have a lot of electrons from there. So electrons is easily available, but the problem is electron, these are charged particles. So there is a interaction between charge of electrons with the material. So always you have to consider the Coulomb interaction, and your calculation will be much more difficult, and you can do it. In some cases you cannot do it, but in most of the cases you can do it, but it is your Coulomb interaction plays a big role, and that will modify your charge scattering, and that will be a problem for electrons. But if I go with ions, then these are also charged particles, but this is a bigger particle. Okay. So compared to electrons, these ions are much bigger particle, and I will show you what is the advantage, what the electrons and ions. And then there are two particles, one is neutrons, another is X-rays, right? X-ray you can assume that these are photons, so photon particles are there, and then you have this is nothing but electromagnetic radiation, and you can have a range of X-rays, and depending on the range of X-rays you can probe different length scale of the material, and you can do that. Neutrons similarly, these are fundamental particle, elementary particle, and then you can do a lot of things. So what are the advantages and disadvantages between X-ray and neutron? I will come to that point, that what are the advantages of X-ray. Instead of some cases X-ray is very advantageous, and some cases neutrons are very advantageous. Okay. So basically this is a particle probe. So you basically think of that heavier element particles scatters from lighter elements. Okay. So if you have photons, to get scattered from lighter elements is difficult. You need bigger. Suppose you have gold atoms, you can easily use photons like X-rays. Okay. There is no problem. But if you have carbon, you have problem. because electrons are the primarily the scatterer of, I will come to that point, how X-ray interacts with the material, and then electrons are the primary scatterer, and then photons are, number of electrons in carbon is 6, whereas in gold it is 58 or 59, right. Okay. So, that means that whenever there is more number of electrons, I have much more scattering. When I have less number of electrons, I have less scattering. Then there is electrons. So, according to the size, if I just go, then electrons are there, and then neutrons are there, and then ultimately ions. So, what I will say that ions are much better probe for lighter elements like hydrogen, carbon, this kind of material. Photons are much better element for this higher Z element, that means this silver, gold and copper, all these things. But there are problems. It is very easy compared to ions, the calculation of the scattered function. Okay. So, that is why these photons are the most useful and most used elementary particles or electromagnetic radiation that is being used for material characterization. So, I will be talking about this photon scattering only from this onwards, but I will show you that how these photons and neutrons are different. Okay. So, how you do these experiments? So, you have so this is a very standard procedure, that you have a sample, you come up with some probe and you detect. So, that is all the experiment. In any experiment in X-ray scattering, you have your sample, you have your probe, which can be X-ray, electron, neutron or ions, whatever it is, and then you have a detection system, which is a detector. For X-ray, the detector will detect in the range of X-ray. For electrons, it is a charged particle, so you detect with a different counter. Okay. And for neutrons, it is also a different detector. So, you have to basically have a probe, your sample, and then you outgoing particle you collect, and depending on the pattern of this outgoing particle, you basically predict what the structure is. So, this is and also X-rays, this is a very short list. So, X-rays is probably has produced maximum number of Nobel Prize. So, lot of people used X-ray as a tool to identify the structure or identify the material and all the other things. So, it has a wide, and this is a kind of preliminary. So, you have Coolidge tube here, you have X-ray coming out, and then you put a, so this is a simple experimental geometry, and you have a crystal here and you get diffraction. So, this is what Sanjay was telling, that you have a diffraction, and from diffraction you can get the structure. So, I will go further in this direction, but before going further, I need to know how X-rays interact with the material. So, this is a very fundamental thing, that how X-rays interact with the material. Okay. So, that is why this basics part is there. So, I will be, you know that X-ray is a electromagnetic wave. So, if you have a plane propagating wave, you can write E0 e to the power I k dot r. So, that is a plane wave definition of electromagnetic wave, and if you have a time dependence, then it will just include k r minus omega t, right, and then you have a time dependence electric field. And then when you have a electron in the medium, okay, let us go to the next slide, then you will see that there is the electron. Okay, X-rays is coming, and I assume that it is a polarized. So, it is in the plane of some plane. Okay. And now, when there is the electron, then it basically starts excite. So, it basically electric field of electron in electric field. So, it will starts to oscillate, and that oscillation basically when it starts oscillating, then it will radiate. So, that is a normal electromagnetic radiation theory, that it will start radiate, and I am collecting the radiation. So, now basically I have a electron and I have X-rays coming in plane wave, and then this starts oscillating, and you are getting the electric radiated field. So, I just need to calculate the radiative field of this electron. So, that will simply tell me how the arrangement of the molecules or how. Okay. So, let us go to the mathematics little. So, if I go back to these slides now. So, basically it will start oscillating and then you will have a basically E by m times the original wave function with a cos psi. Cos psi is basically this angle, right. So, you will start, it will start oscillation and the oscillation acceleration of this electron will give radiative field and that acceleration is basically this one. And so, you can easily calculate. So, these are textbook problem that you are in MSc days. If you just go to Panofsky Phillips or Jackson book, you will see that this is basically the whole thing, that you have E radiative field which is nothing but a constant and then E by m times the whole thing here. And if you divide it with E in, then you will have a this kind of constant which is divided by, which is basically modulated by e to the power I k dot r by r and cos psi. So, when you are here, then you can see the full oscillation, but as you go this direction, you will not see that projection of that oscillation, and as you go here cos psi is equal to 0, then you will not see that electrons are oscillating. So, that is coming here, that it will have a magnitude of the radiated field is basically a constant time e to the power I k r by r. Okay. And this term, this constant term, we call it R0. Okay. So, it is called classical electron radius. So, this term is very important all the time. I will go back to this term. So, your radiative field is nothing but R0 times you had e to the power I k dot r, you had this thing, right, initially e to the power I k dot r. Now, you modified this thing because of we are measuring at a distance r and it will be 1 over r proportional to 1 over r. So, multiplied by a factor R0. So, you do not need to think much, you just say that my radiative field will be R0 times the original electric field with a factor which is basically diminishing at e to the power I k dot r. Okay. So, at k dot r by r. So, that is the calculation. So, basically if you have a one electron, then easily you can calculate the scattering cross section and you can calculate this thing to go this way and you have a R0 square cos square psi, while basically psi is basically polarization factor that I was talking, that if you are here you can see the full oscillations of the electron, but if you come here you will not see the oscillations, and that is why this polarization terms is there. So, basically your scattering cross section is nothing but R0 square. So, if you and there in R0 you have nothing, you have number of electrons and a electronic charge and mc square, this is a constant term, right. So, from a single electron, if you just calculate the scattering cross section, you just say that I have my scattering cross section is R0 square, that is all. Okay. Now, I go little far, because I am not dealing with electrons, I am dealing with atom, molecules and the thin films. So, I have to go all the way from electron to materials. And then the polarization factor, these are very common. So, I do not go into details, but now instead of an electron, now I have an atom. So, I can think of that atom is a uniform distribution of electron cloud. So, instead of an electron, now I am talking about electron cloud, where the electrons are distributed homogeneously, and then I take a small slice within that medium. I take the phase difference between k dot between this wave and that wave, and then I get a wave vector which is called q. So, in diffraction, you in last class you saw that it is the wave vector q, right, in your DHKL and all these things, you always see that wave vector q. So, this q is basically originating from the phase difference between the incident wave and the exit wave, and that you have a q dot r. So, you forget it everything, you instead of electron you can think of that rho r dr is my electron. Instead of 1 electron, now my density of electron is rho r, and I am integrating over the whole entire volume of dr. So, rho r dr is my number of electrons, and then e to the power I q dot r. So, that is all I need to do. So, basically if you just consider an atom, then you do not need to do anything. You multiplied r 0 with the density of the electron within that volume, then e to the power I q dot r you multiply, and then you integrate over the entire volume. So, that is what it is done, that basically r 0 and integration over the entire volume of this electron cloud, and then you get r 0. So, this is called atomic form factor. Okay. So, now instead of a of an electron, now I come to the point that I can have a atomic form factor of material, and that form factor will give me the scattering from the atom. So, I started with electron, now I came to the point that I can calculate the scattering or the scattering cross section from the atom. Okay. Next I have to go. So, here you can see that if you have assumed, it can be assumed as this F0q, this is as a Z. So, basically that will tell you that the Z number of electrons, if more, then the scattering is more, number of electrons is less, then the scattering is less, and that will tell me towards that other slides before, that when you are, it is mostly the electron scattering. So, electrons, whenever I have a material with more number of electrons, I get more scattering, and when I have a less number of electrons, I get less scattering, and that exactly coming from these equations. Now, okay. So, in my previous atomic form factor, I have not considered the any so you know that there are absorption energies. So, I have not considered the energy dependence. I have considered some lambda is coming and some lambda is going out, right. So, same lambda is going out, not some lambda is going out. Then I have not considered h cross omega, which is the energy of the incident wave. So, if I consider the energy of the incident wave as a function, then basically this f of q, the previous atomic previous slide, that this f0 q that can be modified as f0 q plus f prime, which and I double f prime h cross omega, and that these terms are the energy dependent terms, because this will have a effect of the absorption of X-rays within the material. Because if you remember that in X-rays copper K alpha, right, you all use copper K alpha in our laboratory, which is 8 keV, right. But if I come with an X-ray with 8 keV, then what will happen? There will be transition, right. It is a basically characteristic slide. So, there will be transition. So, that needs to be taken care, because otherwise F0 q does not have any energy dependence. It is simply R0 times your electron density. So, that contribution, that energy contribution comes here. So, basically that absorption or the extra scattering, that will, these two factors will take care. And what about I? I is basically gives you the absorption. So, absorption of X-ray is always a factor, and that you have to take care. So, that I take care this f double prime per part. So, there is a big table, you can there is a website cxro.lbl.gov, or there is a X-ray data booklet, where it is all these energies starting from few hundred CV to all the way 30 keV. They have calculated all these numbers, f double prime and f double prime, f prime and f double prime, and when you do a calculation in your material, then you just include those numbers constant, and then you can easily calculate this thing. Okay. So, now so far if I have an atom, I can calculate, and I can calculate the scattering from this atom, and now I am not considering atom, I want to consider the molecule. So, now if I have a molecule, then I have the same thing, you have a similar pattern, calculation. So, I have a molecule, I calculate the phase difference between these two scattering from here, and then I will integrate. But then this integration molecule, you have not same materials here and same materials here. So, you have a different distribution, and that is why we have included not the integration, but the summation. Because you basically can integrate this molecule, this atom 1 and this atom 1, and then you basically sum with a phase factor correction, and then you have this molecular form factor. And then if you go for crystal, it is the same, that instead of just having one molecule, you calculate one molecule, and then you calculate that what will be the phase difference between this molecule and this molecule, and then you include that thing. Then you have a structure factor and a lattice sum. So, this is the basic that you are using in your X-ray diffraction. So, you calculate the unit cell structure factor, and then basically you sum it with for lattice, and then you have the total scattering, and that will give you the diffraction. So, the X-ray diffraction, what you understood, what you basically learned in previous class or previously, it is nothing but exactly the same thing here, what I am doing. Now, so that is the Bragg diffraction that you had in previous class, right. Now, I come to the modification part, that what is new in this geometry. Okay, so, I told you that I have a sample and I have an incident X-ray and I have a scattered X-ray. Now, I want you always have seen that it is the wave vector transfer, that means Ki minus Kf, right. So, and these are Ki, Kf, all are vector quantity. So, that means it has a direction, and you can, when there is a vector quantity, you can basically divide it in 3 components, x, y, or z, or r, theta, whatever it is. But now, let us consider that I have a wave vector q, and that wave vector I want to separate in 3 different directions, x, y, z, and then I have this, if my wave vector is q, then qx is my component along qx direction, qy is my component along y direction, and qz is my component along z direction. And then I want to calculate the relation between with respect to q. So, if I do this thing, then I have a qz, which is 2 pi by lambda sin alpha I by sin alpha. So, this is a vector. If you just go back to your BSc Spiegel vector analysis, you will see that we have done this calculation in BSc, but without knowing that why we have done it. Okay. So, we have done this calculation qz, qx, q, exactly this number, this with these letters qx, qy, and qz, but without knowing that why we are doing this thing. Now, basically you can see that you have a wave vector transfer q, and then that q wave vector is a vector quantity, and that has a 3 component qx, qy, and qz, and exactly this is the thing. So, you can calculate these numbers. And now, why it is important? Because now these things comes to the understanding of physics. Yes. Yeah.
Why the function of k vector is stopped in the second order of function?
Where it is?
First order.
Here?
First next. That is zeroth order, first order, and second.
Oh, no, these are not first order or second order, these are not. Okay. So, these are not first order, these are 2 dependence. So, basically one is q vector dependence, that means your angle dependent. Another is a factor which is energy dependent. So, basically you have form factor is a function of q and energy. Okay. Because that is what I was telling, that when you have molecules which has absorption at say 8 keV, or let us say gold 12.9 keV, 11.9 keV, not 12.9, 11.9 keV. So, when you are coming with an X-ray with 11 keV, and exactly 11.9 keV, there will be a difference in scattering. How you take care? How you take care of that scattering from 11 keV to 11.9 keV? So, basically there you have the absorption energy. So, your part of X-ray is being used to basically excite electrons from lower level to the upper level. So, that you need to take care in your calculation. So, that part is the energy dependent. So, that means there will be a energy dependent term and a not energy dependent term. So, here I am doing the same thing, that I have a no energy dependence term which is F0, and then the energy dependent term which is F prime. It is not differentiation, it is F prime, okay, which is purely energy dependent. So, what I will do? I will calculate the scattering F prime from the database. I will just go back and see. If you see this CXRO web page or CXRO web page or the X-ray data booklet, you can easily get this number F prime and F double prime. This is tabulated. So, whenever I am using an X-ray of 12 keV and when I am using an X-ray of 12.9 keV or I am using an X-ray of 8 keV, and if I know the molecule, I have copper molecule or gold molecule, then I will simply go to that numbers and use, and then I can get the total scattering atomic form factor. So, it has nothing to do with the first order or second order. Okay. It is basically the difference of not energy dependent and energy dependent. Okay. Okay. Now, I came back to, is it okay? Yeah. So, I came back to this point that okay, I have to go fast. So, I came back to this point that when I have a I have this alpha I and alpha f. So, alpha I, let us assume this diagram very carefully, otherwise I will not be able to make it understand for the next whole talk. So, I am coming with an X-ray, let us say in y direction with a alpha I, okay, in the angle, and then I am taking a scattering in a general direction because this is a 3-dimensional object. So, basically I am coming this way and I am measuring it here. Okay. Now, I have a projection in the xy plane. So, that is what this projection qxy, and then I can have a qy component, I have a qx component, and then I have a qz component. This projection along z direction is a qa component. So, and if I do the calculation, then I have a qz is equal to sin alpha I by sin alpha f. You assume that this calculation is correct because you can do it very easily in your home, at your home, and then qx is qy. So, what you can see that there is a chi means that I am coming from, if I go in this direction, if I am coming this direction, I am not measuring in this direction, but I am measuring somewhere in this direction. So, my scattering geometry is not basically in the same plane. I am considering if you see this refractive index on all. So, your one thing is that incident wave, perpendicular, and the scattering is all in the same plane. It is still valid, but I am not measuring the same plane. I am measuring at some other plane, other angle, and that angle is my chi. So, basically I am coming this way, I am measuring it here. Okay. So, now what do I have? Then when you measuring it at some chi, at some in plane angle chi, then I have this qx and qy component, but if I am measuring this coming this way and then measuring here, then I do not have any chi. So, cos chi is 0 and sin chi is 0 also, and then basically I have only qz component. Okay. So, when I am measuring X-ray coming in y direction and measuring in y direction, then I am sensitive only to this vector qz. Okay. Let us first understand that what is the significance of this equation, then I will come to the point that how this impact your measurement. Okay. So, I am coming in y direction and I am measuring in y direction. That means, my angle is changing. This is a simple theta to theta geometry in your powder XRD lab, right. you are coming in that direction, you are measuring in that direction. So, your arms are going in this direction and you are measuring it simply. So, that means you are actually measuring changing alpha I and alpha f, nothing more than that. And then you have only qz component. So, your total q vector is will have only qz component and qx and qy component will be 0. Okay. But if you come in this direction, then you have chi component and then only you have a qx and qy component, this thing is coming. Okay. So, now I understand that how I can make a non-zero qx, non-zero qy and non-zero qz. Okay. Now, what is the implication of this thing? So, this is very important for your any scattering geometry, any scattering experiment. What you want to understand. Now, qz equivalent to qz is your perpendicular in your sample space, right? It's a reciprocal space is a q space and the real space is a sample space which is R space. So, qz equivalent term in real space is the perpendicular z direction. Qx equivalent term is the x direction and qy equivalent term is y direction. So, this part we know. Now, if I measure my scattering in a way that I change only qz, that means I am changing in real space the information in z direction only. Okay. So, I am not measuring any other direction, I am not considering any other distribution in this direction, I am just considering the distribution along the vertical direction of the sample. You understood this thing? Okay. Now, if I want to make a non-zero qx, that means I have to go in this direction, you know that chi, I have to make some chi, non-zero chi, and then you can get a qx and qy component. That means you have a qz, you have a qx and qy. That means in this scattering geometry, you can get information about the in plane. That means in this direction of the sample as well as the vertical direction. So, your scattering geometry will be much more complicated, your scattering pattern will be much more complicated and you have to analyze the distribution of molecules along x direction, along y direction and along z direction. So, by changing the scattering geometry only, you can actually measure where you want to probe. For thin film, now come back to the thin film configuration. What is thin film? So, basically you have a material of certain material, right, certain material, and thin film means is I am talking about length scale of something close to nanometer to maybe 100 nanometer, few tens of nanometer or 100 nanometer. Okay, that's what we call this thin film. And then I want to know the variation of electron, we call it electron density, variation of electron density along the perpendicular plane. Okay. So, if I know want to know the variation of electrons density along this height of the film direction, then I simply forget other things, I will simply do qz scan. If I want to know the variation in the in plane direction also, then I will go simply in other direction and I will do it. So, that is what this scattering geometry is very important. So, it depends on what are the things you want to measure and that will dictate your scattering geometry and that will give you the exact information. So, unless you know what you want to know, then you basically your scattering is totally ambiguous and you will not be able to understand what is coming. So, you can say that okay, diffraction is a separate thing. Diffraction, what is the difference between, okay, I will talk about that. So, now if I have a xy plot where I have a qz direction and qy direction, okay, not qy but q parallel, which is basically root over x qx square plus qy square. So, I have this direction, I have this direction qy, q parallel and this direction is qz. So, if I do only alpha I and alpha f change, no chi change, then basically I am getting points along this direction. So, that is called specular reflectivity. Why it is specular reflectivity? What is reflectivity? Because this is the incidence angle is equal to the exit angle. So, that is the normal reflection, right. When you have a mirror, if you shine a light, then I get at some point I get a reflection. And that reflection, if I calculate typical class 12 experiment, that basically you see alpha I is equal to alpha f, and that is called the reflection. So, when alpha I is equal to alpha f, that we call the QZ scan, and that you will have basically we call it specular reflectivity. But if you want to measure QZ, QX, QY all, then you have a this region which is called grazing incidence small angle geometry. So, then you get information about, so you had a small angles class last yesterday, right. So, basically this is the information you can get, that you will have a particle size information, in plane direction, out of plane direction, all these information if you do a gazing incidence small angle scattering. And if you go all the way down here, we call it gazing incidence diffraction. But what is the difference between this specular reflectivity and this gazing incidence diffraction? This is basically, in one case you have a information along this direction, in another case you are not changing QZ, you are changing along this direction. So, you are totally have a information about the in plane. So, I will talk about this scattering and this scattering. Okay. So, these two scattering I will be talking about, and that is what my aim is next half an hour or so. So, now I have to calculate how to calculate reflectivity. Okay. So, I have this is a light. So, alpha I it is refracted in alpha f, alpha prime or whatever it is, and then you have a. So, this is a strong normal Snell's law, cos n is equal to cos so this is cos alpha is equal to cos a. So, these are nothing new, these are known. Now, for X-ray, the beauty of X-ray is that for X-ray regime, for light, any material, vacuum is 1, diffractive index is 1, right, and any material is greater than 1. So, if you take glass or any material is greater than, but for X-ray it is the opposite. It is for X-ray regime, any material is less than 1 and vacuum is 1. It is just the opposite. Okay. So, what will happen? That means, this is my tensor medium and this is my lower refractive index material. So, what we will have? That means, I get total external reflection, right. So, if I come below certain angle, then I will have a total external reflection from the surface of the material, because my density here is low and density here is high. So, when you material, when wave is coming from higher density material to lower density material, there exists a critical angle, and that critical angle we call total external reflection, and that basically it is there, that whenever we have alpha less than alpha c, then we have total scattering. Okay. Now, for X-rays, that is what we said, that in vacuum is equal to 1 and in medium is always less than 1. So, how much it is less than 1? How much? So, this is less than 1 I am talking, but so basically you have 1 minus delta, and delta will tell you that how much it is lowered. Okay. And delta will, you will see that this delta will depend on the electron density of the material. So, that means that you have a higher electron density material, your delta is more, that means n is more deviated from 1. You have a low electron density material, then your n is less deviated from 1, and that gives you this basically this 1 minus delta higher, close to 1. So, and what is the order of this delta? Any idea what is the order of this delta? It is of the order of 10 to the power minus 6. So, it is not much, like 1.5 for glass and 1, so visible light 1.5 per glass and 1. It is not that. It is of the order of 10 to the power minus 6. So, the external reflection, this alpha c, will be much less than the normal light waves. And how less? It is less than few tenths of a degree, few tenths of millidegree. So, basically normal alpha c is close to, if you use copper K alpha line, then if you have a gold, let us say your alpha c is something like 80 millidegree. Okay. So, this is the 80 millidegree. So, that gives you the information that why I started with grazing incidence. Okay. So, that means, and my angle is this one. Okay. So, that angle is my 80 millidegree. So, I start from 0 degree, almost 0 millidegree almost, and then all the way go to some few tenths of degree or few degrees. But that means that my information is mostly in the regime of grazing incidence, when my angle X-ray of my angle of my incidence X-ray to the sample is close to few tenths of degree or few hundreds of degree, millidegree, sorry. So, that is why this geometry is called grazing incidence scattering geometry. Okay. So, now at least you are clear that why it is called grazing incidence. And then if you do these calculations, it's a delta is equal to 10 to the minus 5 to 10 to the minus 6, and you can see that delta is proportional to the rho electron. Rho electrons basically the electron density of the material. So, basically if you atomic number, if you by this volume, then you get rho electron, and you can calculate this n and beta not, and beta is related to the absorption of the X-ray. So, now I have to calculate the reflectivity. So, this is my once slowly I am going into that direction. So, I have coming with my angle alpha I, and I am measuring at alpha f. I do not have any in plane angle chi. So, I am when alpha I is equal to alpha f, then I have q z component, and then if you do this little bit of calculation in your home, then you will see that there is a q z component. So, we call it q z component in the medium and q z component in vacuum. So, q z 0, when we call 0, 0 is my vacuum, and then when you have a substrate, that means q z s, then you have the q z in the medium. So, it is related to by this equation, and then you can calculate reflectance R and T and easily, and then you can calculate reflectivity, and you can actually calculate that how the X-ray is reflecting from that surface. So, you can measure. So, this is the actual measurement generated or measurement. It is basically you can see that you have a total external reflection up to certain point, and then you have a drop. So, when you have a material, single material, you are coming with an X-ray, you are simply changing alpha I in sequence with alpha f. So, at that alpha f is equal to alpha I, and then you are measuring this, and you will get this kind of reflectivity. And from that reflectivity, you can understand that this is my total external reflection, and if you go back to that total external reflection Q c, you will see that Q c is, this is alpha c is related to Q c with respect to delta, and delta is related to electron density. So, that means that you from this critical angle, you can talk about what is your material, what is the Z of this material. So, if you have a material thin film with polymer like carbon, hydrogen and nitrogen, oxygen, and you have a material with something higher element like silicon, immediately you can see that by measuring this Q c, you can talk about that material. Okay. So, I guess this is completely new thing for you. So, maybe it is a kind of going over the head, but if you have any questions, just let me know, or you are not totally out of sync. Yeah, totally out of sync? No? Okay, good. At least you raised your. So, now if I go back to this, I understand this is not a lecture that basically you will understand everything by having a lecture. So, It is not that. It is a course that is defined to give you some interest and give you the glimpse of the technique, and then when you actually need it, you can go back to your book and calculate and do the measurements. Okay. So, that is the purpose, and I am sure that you will grasp some part, you will not be able to understand the whole part, because this course is something what I am teaching you, what I am giving you lecture is probably 3-4 classes, and that I am just squeezing it in all in 1 hour. Okay. So, now I have a thin film. So, I started with a thin film. So, I have a thin film means I have a 0, 1 and 2. So, I have a vacuum, then I have a thin film of some material, and then my substrate is my 2. So, basically suppose I have deposited some polymer on silicon substrate. So, that is the basically configuration. So, you have vacuum, then you have polymer, and then you have silicon substrate, and then you are calculating. If you just do this simple calculation, you will see that there is a term D. Okay. So, this is a new term that you did not show, but you need to do this calculation. If you do this calculation, you will see that there will be a term containing D, and that D, this term, if you do the reflectivity calculation, there will be cos. So, cos means there will be oscillations, and exactly this kind of oscillations are coming, and from the oscillations what you are getting? You are from these oscillations you are getting the thickness of that film. So, I started with that I need to know the thickness, I need to know the roughness, I need to know the material. So, from this this is a real measurement, okay. This is not generated, this is a real measurement of a polymer film of 140 angstrom, that means 14 nanometer thick film, and then I get this kind of reflectivity profile, and from that reflectivity profile immediately I can talk and that what is the thickness of this material. And I already told you that from this bending I can talk about what is the density of the material. So, now from this reflectivity, just by doing this reflectivity, I can talk about the thickness, I can talk about the material, and what rest? I have another point, that is my roughness. Okay. That will come to the next slides. So, I can have this kind of single layer, or I can have a multiple layer like this, and then I have a complicated reflectivity profile. And then you need to basically analyze like your foolproof you are talking now. So, that means that you have a pattern and you have a model, and then you see whether this model is fitting or not, and you refine back, and then you do again. So, this is a back and forth you are doing, and that is exactly the same thing that you do back and forth, and then you get exactly the density pattern sorry, you get exactly the density pattern what you get what you have in your thin film. So, by analyzing this so far, what we understood that if I have a thin film on my substrate, I can do a reflectivity and I can talk about the density gradient along the vertical direction. What is the density gradient I am talking about? Suppose I have a gold silver multilayer film or copper silver multilayer film, something I do not care. I have a multilayer film, and then I have a different density in copper layer or in gold layer, and I get different variations. And also I have a intermixed layer, right. So, I have a gold layer, so let us say copper and gold, okay. These are the two materials I have on silicon. So, I have a copper layer, I have a gold layer, and what is the different layer and what is the thickness of those layers, I can calculate by simply doing the reflectivity of that material. And then I have another parameter that I did not talk about so far is the roughness, because I have roughness here, I have roughness at the every interface, because the gold will not sit like a like a ideal surface, were truncated at and there will be roughness. So, there will be up and down, and on top of you have your copper deposition, then that will have a basically whatever it's below is there, it will percolate to the next, and then you will have a mixed layer. So, your interface roughness and the top surface roughness, all these are important parameters, and those you need to basically understand, and that you can get it from this reflectivity profile. Okay. So, before that I have a one more slide, two more slide that what are the difference. So, now so far I said that I have a either polymer film on silicon substrate or gold film on silicon substrate. How should I know that my silicon? So, this is a calculation. So, this is my silicon, this blue curve is basically the silicon. Okay. Now, I have a material which is less than the density, electron density of silicon. So, let us say carbon. Okay. So, I have a carbon film on silicon. So, what I will have a, it is a quite thick carbon, and it is a theoretical generated. So, what I have a QC corresponding to carbon, and then I will have a QC corresponding to silicon. So, that means what does it mean? That means that I have a density which is lower than the substrate. So, basically X-ray starts coming if I just keep on increasing the incidence angle. So, at some point there will be a critical angle of with respect to polymer or carbon, and then if I go above that critical angle, then it will start to penetrate through the medium, through the polymer film or the carbon film, but still it is higher than the silicon. So, that means, so this shows that this is my penetration, and then it is higher. So, it is my silicon. So, it goes until then the critical angle of silicon, and then above critical angle it starts to fall. Okay. So, this is my, from this diagram I can say that this is my critical angle of my polymer material, and this is my critical angle for silicon. So, it is not only the substrate, it is also on the film quality and other things. I can talk about the what are the materials I have deposited. But if I have a material which is higher than the electron density of silicon, so let us say gold is higher than the silicon, right. So, then what you will have, it will simply cross, because it is not able to penetrate, because it is the first interface is a gold and vacuum. So, critical angle is much higher, because the electron density is much higher. So, it will cross, and then it will have a, and what this curve is showing, that when you have a density of material which is less than the density of your substrate, then your top convolution of the peaks will be the silicon. And when you have a material, it's silicon means substrate, I am talking about silicon means substrate. Okay. But when you have a material which is higher than the density of the substrate, then your bottom convolution will be your. So, from that also you can talk about that whether the material is your more than the density of your substrate or not. And this is the another thing that you will see, that ideal case you will see 1 1 1 1 1 critical angle total external reflection, and at some point it will start to penetrate. But in yeah. Sorry. Yeah.
Lattice planes are not wide.
No. Okay. Okay. I will talk. I will go. This is an important point. I will talk. So, here you will see that total external reflection coming, and then at some angle it starts to penetrate, and this is the ideal curve, right. So, it is coming and it is going. But in actual case, if I just go back to the previous, this one also, or you will see that this is a kind of bended, right, kind of basically rounding, and also this one here you can see that it is rounded, and also here you can see that this is rounded kind, right. This is not like a sharp transition as you can see. So, what is the effect of that? That is basically the absorption of the material, X-ray absorption. So, X-ray will get absorbed in the material, and that the more absorption will have a this kind of bending. So, that means I told you that n is equal to 1 minus delta plus I beta, right. So, that beta factor you will basically make it round. So, the more absorbing material you will have a more bending. Okay. Now, in your coming back to your question, that I have not yet talked about the lattice, right. But if I go back to this this thing, I always talked about the grazing incidence. That much you are understood, right? Grazing incidence. That means the angle of incident and the angle of diffraction or the angle of measurement is very small. Now, if you do a powder diffraction, what is your angle range? Something like 15 degree to 90 degree, right? And what is this range? Is from 0 to maybe 5-6 degree. Okay. So, when you are coming, so suppose I have placed some balls here, right? When I am coming looking at these directions, then I have say let us say separated it a uniform distance. So, I make a lattice, I can see that each lattice points, right. But if I come all the way to the ground level, I will see only one ball and little bit start to see separation and separation, right. So, when you are going into the grazing incidence, then you will not see individual balls, but you will see a gradient of these balls, right. It is a distributed projection, it is a projection of that ball in that X-ray direction, and that basically elongated over the whole sample. So, instead of lattice, you will see electron clouds. So, you will not see the electrons separated by a lattice spacing, but you will see electrons are like uniformly distributed over this length scale, and that is why we call it electron cloud, not a separate electrons or separate set of electrons. So, that is why there is no lattice here, it is the uniform density. We all talk about density of electrons, and density of electrons means that it is not separated in a discrete fashion, it is like a continuous, because X-rays are coming at so shallow angle that it will not be able to distinguish between lattice 1 and lattice 2. Okay. So, that is why you do not see lattice. Yeah. Polarizability I have not considered here. Polarizability is also anisotropic here, but polarization is kind of okay. For this case, your polarization X-ray reflectivity with polarized light, nobody does it, because you are not sensitive to that polarization. But what you will have if you go in synchrotron, synchrotrons are mostly polarized in the horizontal plane. Okay. So, I told you this cos psi. So, if you go in this direction, then your psi is 0. So, that means cos psi is 90. So, you basically have a no scattering, right. So, you have to choose your geometry in a way that you do not scan. You can scan. Okay. Let us say I have a material, right. I can come X-ray with this direction and then measure in this direction. So, this is my scattering plane. Okay. So, my incidence angle is changing this direction and my scattering angle is changing in this direction. I can have also X-ray in this direction. So, I am going in this direction and this direction, right. In synchrotrons, if I come along this direction and do a measurement along this direction, then I have to include that polarization factor, because my polarization is going down because my polarization in this direction. Okay. But if I do into lab scale, my lab scale this is not polarized. So, everything is unpolarized light. So, I do not care whether I am doing this direction or this direction. So, in lab you will see all the reflectivity set up. So, if you use Bruckert, you will see that it is in this direction. but if you see the Rigaku instruments, then you will see this is vertical. It does not matter, because it is the polarization is not there, it is basically unpolarized light. But if you go in synchrotrons, then your reflectivity have to be taken by in this direction, because if you go in this direction, anyway you can go there, because you are not going in 90 degree, no? You are going in very small, so 5 degree, 6 degree, maybe 10 degree. So the factor of cos 10 is very less, though you have to consider that, but you do not need to have a much, but if you go in go really high angle, then you have to consider that. So now the next term, that is the so now the next term, that is the density roughness, right. So there will be a so how we do that, we basically put a Debye-Euler factor. So basically kind of damping factor, and that damping factor is something like this. So we call it Gaussian roughness. So if I have this roughness, if I plot it the weightage function, then it will be like this. So we basically simply multiply this reflectivity with the error function, and we get the roughness. So I started with the thing that I can measure the thickness, I can measure the density of the material, which is the characteristics of the material property, material, actual material composition, and the roughness. So all these things I can calculate from this reflectivity profile. Okay. Now, so this is the effect of roughness, that you can see that if I have a so if I have a roughness, then it goes like this reflectivity. If I do not have roughness, then it goes like this. And so this is the reflectivity from water surface. So water is supposed to be roughness 0, but it is not. Actually there is a thermal fluctuation, we call it capillary wave fluctuations, and that because of that fluctuations there will be roughness, and you can see that actual roughness is 0 roughness is going this direction, and it actually falls in this direction. So that means there is a roughness, and you can calculate the roughness from the water surface. Okay. So this is another thing, that typical reflectivity profile that. Okay. Now what you do in your experiment, what you do, you basically measure the sample, and then you try to fit that data. Okay. So this is a kind of a little bit of job, because you need to model, just like diffraction, you are modeling your space group and space and all these things. Here also you need to model the density along the vertical directions, and then you can generate the reflectivity profile, and then also can. So these are details modeling, and then I was talking this CXRO website, that cxro.lbl.gov. You can get all the parameters for f_w prime, f0 and f prime. So all the f prime and f double prime, not f0, f prime and f double prime from this link. Basically this atomic scattering factor to X-ray diffraction table. And there is another model that I am not going to, because I am running out of time. So I have only 10 minutes, right? So I am supposed to go by 3:30, no? Yeah. So I am not going to into details, but you can also go into these are higher level of fitting methods. So you can go for the model independent fitting, and then you can actually whatever the reflectivity profile is there, you can actually model. And this is the kind of reflectivity profile you can, and you can model it. This is for the polymer surface that you can talk about, that you have a. So next topic is that grazing incidence diffraction, that the last topic I was talking, and then I will quickly show you what is the diffraction, what is the synchrotron scattering. So grazing incidence diffraction, you come with an angle which is also grazing. So basically you are very shallow angle, something like close to few tens of millidegree, and then you, instead of going in this direction, you are going in the in-plane direction. That means your Qy component is more important, Qy or Qx. You forget about Qx, because Qx is your Qx is in this direction. This is Qz, Qy, and this Qz, Qx is along the detector. So you forget about that. You basically sensitive to Qy, and you can talk about the. Now, here your case is that you are coming at very shallow angle, that means the grazing angles, but your measuring angle is very high, something like 15 degree, 16 degree or 20 degree. So, that means that you are sensitive in this case, because your total scattering vector is so high that you are sensitive to lattice. So, now you are talking about that how in plane lattice are distributed. So, instead of a vertical direction distribution, now you are talking about the in plane distribution of the molecule, and you can talk about the what are the phases of different molecules and how it is they are done. So, if you have a 2D lattice, you will have a reciprocal rods, you will have a basically reciprocal space, it will have a rods. But if you have a rod like molecules, so somebody was talking about liquid crystals, so these are rod like molecules. So, if you have rod like molecules, then your reciprocal space is like a disk. And if you have a distribution of a molecular basically arrangement of this kind of rod molecules in this fashion, then you will see that you will have a rod with some discrete. So, basically you can talk about diffraction, this is the real diffraction, liquid crystal diffraction. You will see that you can see this kind of, and if you probe, this is the reciprocal space, and so if you go along, this is along QZ direction, so you will see that here you have a bright spot, then low, and then bright spot, and then low, and then something like that. And if you go along this direction, so you can map your liquid crystal or so. What is the difference between liquid crystal and the, so first thing is that what is the difference between liquid crystal and a normal crystal? Because of this anisotropy of these molecules, now you have another degree of freedom, that is the orientation. So, liquid crystals are liquids because it does not have a long range translational ordering, but it has a orientational ordering. So, that makes it a crystal. So, when these molecules are oriented in a particular directions, long range orientation, then it is called the oriented phase or the liquid crystal phase, and then you have this kind of diffraction, and you can get this kind of diffraction from there. Only thing is that these are in Q space, so basically either you go along QZ direction or QS direction, and then you can actually have, I do not want to go there, you will have this kind of diffraction. Okay. So, here you can see, you can map what are the crystal lattices are, and then you can actually calculate that what is the difference between this lattice and this direction and all. Okay. So, liquid crystals or these kind of rod like molecules you can map, and you can get the diffraction using grazing incident diffraction, because you are talking about the in plane orientation of the molecule. You are not sensitive how these molecules are vertically, you can do that, but it is, if you go in plane direction, you can talk about the how these molecules are basically standing in the in plane, and if you go along this direction, then you can say that how these instead of lattice, how this arrangement of these molecules are basically varying along these directions. So, these are the real data that you can see, these are the kind of rod like molecules, and you can do diffraction. Okay. So, I am not going to this thing, I will quickly go over to the synchrotron. What is synchrotron? Okay. So, synchrotron is there any lecture on synchrotron? No, no, right. So, in synchrotrons, what is the difference between lab source and synchrotron source? So, lab source, we know in terms of intensity, we know that it is 10 to the power 6 to 10 to the power 7 photons per millimeter cube, blah blah blah, solid angle and all these things. But the major thing is that 10 to the power 6 to 10 to the power 7 photons, right, per second. But in synchrotron, you can go something like 10 to the power 14, 10 to the power 15 kind of photons per second. So, that is why these synchrotrons are brighter source of your X-ray. So, that is the basic thing, brighter source of your X-ray. And then how you produce? You have different kind of mechanism, we call it basically active elements. Though basically you have a bending magnet. Bending magnet means when you have a electrons. So, how you produce this synchrotron radiation? In your X-ray tube, you basically impinge high velocity electron on cathode, anode material, and then from there you get the X-ray, right. In here, you basically have a stream of electrons, and when you stream of electrons, when it basically bends, that bending means acceleration, and acceleration means it will emit radiation. So, when you have a energy of that electron is in the order of GeV, giga electron volt, then your emitted radiation is in the X-ray regime, and that is the synchrotron. So, you are starting with stream of electrons, you bend it and then you get radiation, and when you have a stream of electrons having energy of few GeV of the order of GeV, then the emitted radiation is in the regime of X-ray. So, that is so basically there are you have a dipole. So, you dipole means when you have electrons, then if there is a magnetic pole, then there will be a bending, right, the Lorentz force, and there will be whenever there is a bending, there will be radiation, and that radiation is synchrotron radiation. So, why it is synchrotron? Because it is a synchronous way it is coming. So, that is why it is synchrotron, and then you have so how it is different from bending magnet to wiggler or undulator? Here you have a single bending, here you have a multiple bending. Multiple bending means you have a small magnets and electrons is like oscillating. So, electrons each time oscillates, it will emit radiation, and if this oscillation, this phase and the next oscillation phase is in the same phase, then it will coherently add. So, basically each bending will give you addition, 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 and then number of bending, depending on number of bending, you will get more intensity. So, that is what this called undulator and wiggler. And then this kind of synchrotron, you have a basically booster ring where you energize the electron and then you project that electron in the big ring, and then you have undulator, bending magnet and all these things, and from there you can get synchrotron radiation, and from there you can set up your lab and then you can measure. So, this is a kind of brief summary, and this is actually one undulator that basically you can see that these are small tiny magnets, and these electrons are oscillating like this, going in this direction oscillation like this, and the periodicity of that oscillation matches exactly with the phase of the emitted radiation, and that will give you the bright source radiation along this direction. Okay, so I will stop here. I think I will not go into more time. So, basically you have a bending magnet here intensity, and you can see that your intensity is going of the order of 10 to the power 5 times more if you just use your undulator, and then you can have it. Okay. So, kind of this is a brief introduction, and now if you have questions or if you have anything to understand, just let me know. Okay. You did not understood everything.
As it is not the lattice moment, but the electron flow,
Yeah.
how the shape of the orbitals are.
No, you are not talking about orbitals. So, you are not talking about orbitals. When you are talking about orbitals, then you are doing spectroscopy. So, basically you are in your scattering geometry, you do not need to think about those things. It is in which cell you do not care. You consider, you see that it is the Z. I never said which cell, what K cell, L cell, M cell, I never said anything. I said number of electrons, Z. Okay. So, and Z is the count. So, I do not need to think about lattice, I do not think about your which cell I am coming up. So, if you are talking about the cell and other things, then it becomes spectroscopy, and then it is X-ray spectroscopy. So, there is a photoelectron spectroscopy, OJ electron spectroscopy, and those are the things. Scattering, you do not need to think. Okay. Yeah. Hmm.
Sir, like we are making a nanocomposite of by using a polymer matrix. Like any film, we are making like polycarbonate or PB film, and we are making a nanocomposite by using some fillers. And after mixing it, and after the fabrication of complete fabrication of polymer film, we want to just check its surface morphology, like how much smoothness it is having or roughness it is having. So will it give all the details?
Yeah, yeah. Your reflectivity is the best technique if your roughness is of the order of nanometer. If it is more than nanometer, then you will not be, because you can see that roughness is killing your reflectivity. So if you have more roughness, you will kill your reflectivity more, because that's the normal, right? If you have a mirror, you are coming with a light, you can get reflection. But if you have a rough thing, let's say white paper, you will not get reflection, because the roughness is much more, right?
Yes, sir. If we are operating our X-ray machine at a more voltage, will it destroy or will it destroy?
No, 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 no. There is a damage. X-ray damage is definitely an issue, but not for lab. Lab X-ray is way down. So 10 to the power 6 is not going to kill your sample. So if you go in synchrotron, definitely you have to move your sample all the time. You have to run behind your sample so that you don't basically burn your sample. You will have it. But then there are something like you reduce your oxygen content in the environment, and then you can reduce your burning. Okay. Yeah. Yeah, of course. Yeah, it depends on Z. Okay. So scattering cross section depends on your Z value. Okay. So if you have so when you are talking about electron clouds, then your Z includes all the elements. Okay. And you are talking about the variation of this Z along this direction or along this direction, whatever it is. But if you have a composite material, like a molecule, no? H2O. So H2O, H has 1 electron, whereas oxygen has 8 electrons. So you are not sensitive to 1 electron or 8 electrons. You are seeing the total 17 electrons. No, not for the composition of individual molecules, not from the composition. So because basically you are seeing what you are seeing the average. So how can you measure the individual? So when you are seeing the average, then you will measure the average, right? So that you will not be able to see. But it gives you some idea about that where the critical angle is and how it is coming. So that way you can get it. Yeah, yeah, and okay, anything more? Okay, thank you.
You can come here.
So good morning. Today we start our discussion on the scanning electron microscope, and we will have 2 lectures today, 2 guest expert lectures, followed by a lab, and tomorrow we will do the same thing. Again, we will cover different topics. So today's 2 lectures will be given by Professor Chandan Srivastav. He is a professor of this department at Materials Engineering at IISc. And he does his expertise ranges in various aspects of material science and engineering, but he is also one of the leading experts of electron microscopes. So whether it be a scanning electron microscope or transmission electron microscope, he is an expert of that, and it's really our honor to have him give these lectures. He has agreed to it, even though it was a little bit, fitting the schedule is a little challenging, but he has agreed, and he will give 2 lectures today, one at now, and then another one after the coffee break. We will continue with the same idea. This is again should be an interactive session. He will go with a speed, but if it is little faster than how you like, please stop him, ask him questions. Again, he is really an expert in this field. Whenever I don't understand anything about electron microscope, I go to him. It's also my pleasure that his office is just next to mine, so I do bother him all the time. But he would like you to ask him questions. That's really the spirit that we have been doing. So please continue that. We make it as interactive as possible. So with that, Professor Chandan Srivastava.
All right. Is it fine? All right. So fine. So my name is Chandan Srivastava. I work in this department, and so welcome to IISc. So what we will do is that we will try to understand something about electron microscopy, okay, and specifically scanning electron microscopy today. How many of you have seen a scanning electron microscope? Okay, so most of you have seen. Okay. And if you have not seen, you will see it today in the afternoon. So we'll start. So I'll be using the board also very much. So we'll lift this screen whenever I want to use the board. So this is a lot of scanning electron microscope images. So so we can make this session interactive. Can somebody tell me what it is? It's an insect. What is this? Very good. What is this? Some rust. Some deformed thing. What is this? Some spherical thing. Very good. Now if I bring you inside this room and I put a band on your eyes and I ask you to touch the screen and tell me what this is, can you tell? No. You cannot tell that this is an insect. Everything you will say that it is a plain board. So what is specifically making these things make sense in your brain? The intensity variation in the image, which is basically making you think or making your brain perceive that this is an insect and this is a sphere and this is some kind of a edge and this is a apex. So what is happening is that this intensity variation is what is creating an image, and that's what the basic idea of scanning electron microscopy imaging is, and that we are going to solve today. Okay. So again I will use this image very often. This again everybody will see now you know that it is the intensity variation which is doing the magic. So by touching this thing, it is a 2D, and in this you will see different kind of intensity variation. So you will see that there are some raised platform which is here, which is having a certain intensity, and these are there are some dark features here which are basically the flat areas, and this part of the image is basically having more intensity than this part of the image. Okay. And that combinations of different kind of intensity is making your brain think that this is a spherical thing with some kind of a morphology. Okay. Now when you are looking at, so first we'll come to the imaging later on. Now what happens when an electron falls on any material? Okay. What happens is that the material, say if this is the sample and if there is an electron beam falling, you get several kinds of signals out of that material, and these signals are basically called secondary electron characteristics X-rays, visible light, backscattered electron or J electron, and then some of them cross the sample and they go on the other side. Okay. What we will not worry about all these things in this course. Okay. We will only worry about the signals which you are seeing on the top. So, if you happen to have a notebook, you can write down few words. Okay. Please, you can write down the word which is called secondary electrons. Okay. You can write down the word characteristic X-rays and you write down the word backscattered electrons. Okay. These three words, and don't worry about all any other word. We will be working on only these three words. Okay. And these things are generated when electron falls on the material. Now, electron basically has two different character. One character is a wave and other character is the particle. Okay. Now, wave, and so when we are mostly dealing with scanning electron microscope, where we are only bombarding the electrons on the sample, okay, then we are mostly looking at the particle nature of the electron. Okay. If we are worried about the diffraction, you have read X-ray diffraction for last 2 days, right? Then we are worried about the wave character of the electron. So, in this course for the next 2 days, we are mostly going to take the particle nature of the electron into account for understanding the scanning electron microscopy. Okay. And this is, and the debate is very large in case of particle and wave theory, but we will not go into the detail of that, right. So, Niels Bohr was once asked that can he comment about the particle and wave nature of electron. So, Niels Bohr told that the electron behaves as particle on Monday, Wednesday and Friday, and rest of the days it behaves like a wave. So, it is extremely complicated. So, let us not worry about it. So, we will take particle nature of the electron. So, we end that debate here. Now, what I will do is that I will try to raise this screen and I will use the board. Is that fine? Because first let's understand, make a construct of a scanning electron microscope. If you understand, if you want to understand a person's nature, you have to first meet the person. So, let us just meet the microscope. So, we will raise the board. Yeah, light, we have to have pen and put my light on. Also, please keep asking questions. So, what we will do is that we will use the board for some time, and these slides I will leave with Professor Praveen Kumar. You can take this slide and keep it with you. Do not put that slide on LinkedIn or on X, because these are all taken from different books. So, it will be a copyright violation. You can use these slides for your own consumption. Okay. So, if you have, so what we will do is that we will construct an SEM, okay, and there are few words here that SEM is what it is, scanning electron microscope, right. So, it is called scanning, and this is electron and this is microscope. Okay. What comes in your mind first thing when you hear the word microscope? Okay. So, the first thing that comes in the mind is lenses, right? Any microscope has lenses. Now, when the word lens comes in your mind, what comes in your mind next? Sorry? Glass lenses, of course. And what else? What is the function of a lens? Magnification. Magnification is the word that comes in your mind. Is there any other word that comes in your mind? Zooming, resolution, very good. Now, interestingly, all the electron microscopes have lenses, okay, and if you go to many of you have seen a scanning electron microscope, all the lenses in the scanning electron microscope, they never do any magnification. What do? They do demagnification. The job of a lens is also to demagnify. Don't underestimate the demagnification part. So, what is demagnification? So, we have to do demagnification. Have you ever done demagnification? Huh? So, if you take a lens and you put a paper and then you take the sun and then you converge it to a point, the paper burns, which is the demagnification. So, all the lenses, so keep this, so all the lenses do demagnification. So, now let us construct an SEM. I will use this side of the board. So, for that first we need an electron source, and this electron source is basically a tungsten filament. Please keep writing in your notebook. I think it is a good idea. Okay. Something you can take it from. Now, this tungsten, now we are not going to go into a lot of technicalities, we will just make an overall construction of a microscope. So, that, and if you write it on your notebook, that will get in your mind. And this tungsten filament is basically heated, and when this is heated, it gives out electron. Basically, the work function is exceeded and the filament will give out electrons. Okay. Now, these filaments are basically of two different kinds. One is thermionic, which gives out because of heat, another is basically it is called a FEG source, field emission gun, and that gives out because of the field at the thing, but that is not important, that is detail. So, once you get a tungsten filament, it actually gives out certain amount of electrons. Okay. And then what you do is that you have to focus. Now, these electrons are coming as a shower out of this tungsten filament, and what you have to do is that you have to converge the electron to a point, and to converge the electron to a point, you apply a negative potential right after the tungsten filament. Okay. And then that makes this electron path change. Okay. But electron is a negatively charged particle, and it basically converges it, and there is another positive potential then that is applied, and this positive potential pulls this electron downward and it converges to a point. Okay. So, this is the way you can actually pull an electron out of a tungsten, give it a negative potential to converge and a positive potential to come down. In the afternoon, when you will go and see the SEM, make a note, this potential is called an operating voltage. So, that is, you will see that it is about 30 kV or 20 kV and those things. So, when you do the practical, you will see those numbers in the afternoon. Okay. Now, what you have done is that you have produced electrons and you have also converged the electrons to a certain point. Okay. But the typical dia of this point would be around 50 micro 50 micrometer, which is a huge number. For now, take it as a huge number. You will see why it is a huge number in some time. Okay. Now, what is done is that now then there is a certain amount of lenses, and let's just draw a lens here. And these lenses are called condenser lenses. Okay, and you can write down this word condenser lens. The job of the what is the condenser lens do? It condenses the very good image of the first crossover. Okay, this is the first crossover. This is called the first crossover. In a typical textbooks, you will see this word. Okay, everybody is with me. Okay, now what is in an optics? Okay, what is the definition of magnification? Size of image by size of the object. It is magnification. Magnification is an English word. Don't get intimidated by it. Okay. It just magnification is image size by object size. That's it. The other way of saying is also image distance by object distance. If you do the symmetry, you will get it. So the magnification is the image distance by the object distance. And so what is demagnification? The object distance by the image distance. So if I take this lens and I make an axis of this lens, why this lens is in a very weird kind of shape, I will tell you in a minute. Okay. So if I take the center of this image and then I take this distance here, this is D1, okay, and I use this lens to demagnify this image into, if I use this lens and I demagnify this is here and use this distance as D2, okay, then that would be the, so how much will be the if this is again formed here, then what is the demagnification? Object distance by the, so what is the object distance? D1 is the by D2. So what we do is that we demagnify the beam, similar to the point that if you take the sun, you can use a lens to demagnify it. Okay, and we keep doing this demagnification. Now, interestingly, we have to also find out how the electron microscope lenses work. Okay. Now, if I ask you that can you create a magnetic field, can you create a magnetic field? Sorry? Yes, very good. Very good. By using a coil, so you just take a and you wind a coil, you take an iron core and you wind a coil, okay,
And supplying the
electricity, very good. So, you make a current go and that will create a magnetic field here, which is a fringe field. It will create a magnetic field around that and that field is a fringe field, okay. And that is what this is. So, in electron microscope these are wires and we pass current, and these are wire and we pass current, okay, and that creates a magnetic field, and that magnetic field is basically, this is the magnetic field, okay. Now, what we do with a magnetic field, how can you change the direction of electron using the magnetic field? Yes, you can change by something called a Lorentz force, which is F is into E into V cross B, where which is VB sin theta into E. That means that the electrons, if this is the field, curved field, and if the electron is going in like this, then this force will act. This is the velocity of the electron, which is the field, is the direction of the field, this is the charge. And let us not worry about the math, okay. I do not want you people to sleep. So, let us just, we will not get into too much math. So, what happens is that this field will essentially cause these electrons to converge to this point, okay, again. And now this point, okay, is a demagnified part of this, demagnified image of this first crossover, okay. So, what is the image? Image is also the electron, the object is also the electron, very good. Now, if I increase the strength of this magnetic field by increasing the current in the wire, horseshoe magnet, okay, then I can increase the force. If I increase the force, then this crossover will move towards the magnetic field, towards this lens. If this crossover moves towards this lens, okay, then will the demagnification increase or will the demagnification decrease? It will increase. So, object distance is, sorry, image distance by object distance, the demagnification is the inverse, which is the object distance by the image distance. The image distance is decreasing. What is the image? This is the image and this is the object. So, if the image distance is decreasing, the demagnification is increasing. So, if the first crossover was 50 micrometer, I can increase the current in the condenser lens and make this electron beam image shift towards the lens and make it smaller. When you do the practical in the afternoon, this is called a spot size. This point is called a spot size. You can note it down. Okay. Now, in an electron microscope, there are nearly in a scanning electron microscope, which has a very high quality, there could be 3 condenser lenses, or there can be 2 condenser lenses sometimes. There is never only one condenser lens, there is always more than one condenser lens, and the job of all these condenser lenses is to make the beam smaller and smaller. Why? We will see in a minute. make the beam smaller and smaller and smaller. So, let us just add one more condenser lens. I will just do this is small diagram here, and we have one more beam which is even smaller than this, and this is smaller than this. We are trying to make the first crossover smaller and smaller. We are, as we take the sun and we use a lens to make it a point, similarly we have to y will come to the point. Now, once we have got the beam very small, then we make it fall on the sample. So, we make the beam fall on the sample. Okay. And when this beam falls on the sample, then we generate a different amount of signals. All right. Now, somebody told the word resolution, okay, and there is also a word called magnification. So, till this is okay, fine, and we will come to this thing again in a minute. We keep this parked aside. Let us just talk about these two words which are highly misunderstood in a certain way. Okay. Now, the question is that what is resolution? Can somebody tell me what is resolution? Sorry? Clarity of the image. Okay. Size of the image. To distinguish to image quality. Okay. Okay. Fine. So, let me do something. So, what I will do is that I will go to this wall and I will make this wall little, I will put 2 points in this wall, okay, and I will go and stand here. I am trying to trick the camera. I do not want to be recorded. Now, as if you are standing here, can you see those 2 dots? No, you cannot see those 2 dots. So, with these conditions of imaging, and what is the camera here? My eye is the camera, and this room is the lighting, size of this room, this distance are the conditions which is, and my camera is my eye. I cannot make out that there are 2 points. In fact, I do not even see any point. So, I move towards the wall. So, I keep moving towards the wall, still I cannot see. Okay. My camera is not catching it, but then I move towards the wall again. Okay. Now, again I can see the point, I can see that there is a dot, but I am not really sure whether there are 2 dots or 1 dot. Okay. Now, again I move little forward. Now, I can see that there are 2 dots. Okay. Now, take this distance at which I can see the 2 dots. Now, this is the conditions of imaging, my distance from this wall, the lighting, if I take out my specs, I cannot see. With my specs, my camera with a specs, I can make out there are 2 dots. Now, I have resolved the image. Now, if I move more nearer or if I move less nearer, it does not matter anymore. Okay. So, this is the condition of the resolution. Okay. And this is also the condition of the required magnification. let's not worry about, but the resolution is clear, right? So the resolution is how best you can make out two different objects, is the definition of the resolution. And that definition basically depends on the condition, very good conditions of the imaging. If your eyesight is much better than my eyesight, you may be able to achieve that resolution just from here. Okay. So that is the definition in a strict sense of microscopy, that is the definition of resolution. Okay. Now the magnification and resolution are basically in a way connected, but what you are actually looking for is only the resolution. You are not looking for the magnification. Okay, we will see why. Now suppose that I take this mobile, everybody has a mobile, right? Now what I do is that I start my camera and I take an, I shoot that camera on the whole class, okay. Then the whole class, now this camera which is in this mobile has a certain pixel, this is m by m pixel, let us say 1000 pixel by 1000 pixel, you just pick a number, okay. If I shoot this thing to the whole class, then the whole class is projected on the screen. Now if I keep moving towards him, okay, please don't get alarmed, if I keep moving towards him and I'll move really close to him, okay. Now this part of the class is cut out, okay, only this part of the class is there. Now I keep moving now, the only he is on the class, this all part is cut out, this all part is cut out. Now if I move really near to him, then I can see his shirt, only one button in his shirt which is in the camera, okay. So what is not changing? The camera is not changing. The amount of information that is put on that camera is now changing. So the camera is still 1000 pixel by 1000 pixel, but now only the shirt button is being projected on that 1000 pixel by 1000 pixel. So now I say that I have a magnified image of his button. So what is actually happening is that now the question somebody will ask that how much near can you move to that person, okay, that the question. You keep moving nearer camera to that person, why, how much near you can go? No, the answer is that if he tells me that my button is little loose, okay, and I cannot see down, so I can move the camera near to his button till I see the two threads which are broken. So after that, how much nearer I go, how much nearer I don't go doesn't matter, because I have solved the problem. So when you use as microscope, you use the magnification till you have enough resolution for the information. That's it, okay, in a practical way. So if I am standing here and if I keep moving towards that wall, I am increasing the magnification. I am increasing the magnification in my retina till I see the two dots, and now there is no point in increasing the magnification because I am able to resolve the information. So in electron microscope, that is something that we will get to, okay. So this is the definition of, now of course it has an optical sense, it has a much other definitions, but let us just be practical. Now let us get back to our image here. So the electron now falls on the sample, okay, and there is also a word called scanning electron microscope. Why it is called scanning electron microscope? it is scanning the surface of the sample. So, if this is the sample, so or this is too big, if this is the sample and if this is the electron beam, then the beam is hitting at this point and it is generating all the signal. What signals we will see in a minute. Then it is hitting and it is like scanning like this, okay, and it is scanning so fast that you are seeing one image. It is like when you have a fan, when the fan is going at full speed, then you see a one circle, okay, you do not see one. So, that is called scanning. So, what is actually happening is that there are deflection coils, but do not worry about the deflection. This is making that beam hit here, 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 and it is this is like hitting like this. It is scanning very fast. So, let us now worry about what happens when it hits the sample at one particular point. Okay. Now, if you take have you ever seen a cricket ball which is the leather ball, which is okay, and there is a tennis ball. So, if you take a leather ball and if you throw it on the wall, okay, and if you take a tennis ball and if you throw it on the wall at the same force, will you see a difference? What difference would be? Sorry? Go on. Bouncing will be different. The one which is the tennis ball will bounce much more than the leather ball. It will just hit the thing, it will break it or fall down or something like that. So, there are two different kind of interactions. Okay. In one interaction, which is the leather ball interaction, the energy is completely given to the sample, or energy is given to the wall that breaks the wall sometimes and the ball falls down. Okay. That is called an inelastic interaction. Okay. If you take a tennis, very good tennis ball, good is not a word, but let us not worry about the specifics too much, and the ball bounces back into my hand with almost the similar kind of energy, then it is called an elastic interaction. Inelastic interaction and elastic interaction. Okay. So, basically, if you are going for lunch and you see somebody whom you really want to meet, okay, you will go and shake hand with that person and stop there. Okay. If in the second case, if you are going for lunch and you really do not want to meet that person, you will just go like this. So, the first, this is called an elastic interaction, that is called an inelastic interaction. When you have stopped, your energy has been completely stopped, your motion has been stopped. Okay. So, similarly, if you take particle nature of the electron, let us not worry about the wave nature of electron at this point of time. That interaction can also be elastic interaction and inelastic interaction with the atom. Okay. So, let us just see how that thing is. So, elastic interaction and inelastic interaction. So, suppose that you take an Bohr model of atom, okay, and this is one atom, let us suppose, okay, and there is an incoming electron, let us just call it EI. Okay, again, just it has been 1 hour, so relax. Okay, don't get too stressed about you really don't need electron microscopy to be happy in life. Okay, so sit down and enjoy. So, if this electron comes in, it comes in with a very high velocity. Why it comes in a very high velocity? Because this has been accelerated with this positive potential. Okay, so it is coming with a very high velocity and it has a large amount of energy. And if this electron comes in and it hits this electron, which is in the innermost shell or any shell, let's suppose, let's not worry about the again too much complicated things, and this electron is ejected out, then this electron is called a secondary electron. It's called secondary electrons, and this is called incident electron. Okay. Then what has happened is, and this electron will actually lose some of its energy, the incoming incident electron, in making this electron go out of the atom, and this electron will now continue its path into the sample. Okay. This interaction, in this interaction, the incoming electron has lost a certain amount of its energy to kick one electron out of the atom, and this interaction is called an inelastic interaction. Let us see what is elastic interaction. So, suppose again there is an atom and these are electrons and this is basically EI. Okay. Okay. Now, have you taken, if you take a thread and you tie a stone at the end of the thread and you do it like this, will it go in a circle? Right? Why it will go in a circle? Because the thread you are pulling it inside, but because of its velocity it wants to go in a straight line. So, it tries to go in a straight line and it goes in a circle. At any point it is going in a straight line and eventually it will go in a circle. So, similarly, if this electron is coming and it does not interact with any of these electrons, but it has the force of the nucleus which pulls it towards the nucleus, and then that basically causes this electron to turn. See, it will go down because it has a very high velocity, but the pull of the nucleus is going to turn it and it goes out of this again in this direction. Okay. So, there is no interaction, there is no hitting of the electron by this electron, but there is a charge interaction because of which it changes the direction of the incoming electron, and this electron, this interaction is the elastic interaction. Now, let us just look at some energy values. The energy of this, now this electron which has been generated by the turning of the incoming electron without any interaction with the sample electron is called a backscattered electron. Okay, so, this is no longer called EI, it is called a backscattered electron. So, BSE is basically backscattered electrons. Now, now to strictly speaking, the backscattered electron energy will not be equal to the EI, because when the charge particle accelerate, they change the direction, velocity is changing direction, they give out radiation. Okay. So these two energies will not be same, but there will be a difference, but that difference will be not that great. At this point of time, you can take that thing. Now, if you see this image again, suppose this electron is knocked out from its axis, that will create a vacancy in this, and this electron from the outer orbit will jump to this orbit, and that would lead to the generation of X-rays. Okay, and which are called characteristic X-rays. Why it is called characteristic X-rays? Sorry? Yeah, because it is the energy value is specific to that particular element. Okay, that is it is called, that is the reason it is called characteristic X-rays. So now if we, I will use this. Now the typical energy of this, now when a secondary electron comes out, it has to overcome the pull of the nucleus, right. So nucleus is positively charged, the secondary electron has to overcome the pull of the nucleus. So the energy of the secondary electron when it has come out of the atom will be very less, and that is very fundamental in imaging in the SEM, this aspect. So this typical energies of the secondary electron will be 50 eV, and eV is a unit of energy. It just means that the amount of energy when one electron crosses 1 volt potential. Okay. You're tired? So let's just see. So the elastic scattering gives out backscattered electrons. And inelastic scattering gives out secondary electrons and X-rays. This we understood. Now we will get back to the slide. Now we will try to decode the image that we saw the first time. Organize some of the signals. Okay. We can now recognize the characteristic X-rays, we can now recognize the secondary electron, and we can now recognize the backscatter electron. Okay. Now let us see this image. I will use this. Is this part of the board visible to everybody? Okay. No, put on the light. So now this is a secondary electron image. Okay. Now what I told you that now let's suppose that this is the sample which is made up of several kinds of atoms. Thus everything is made up of atoms, okay, and an electron beam falls on the sample, okay, and that electron beam now creates a zone in which there is a certain disturbance, okay. So in that volume of the sample it creates all the signals, and that is called an interaction volume. So for example, if you take a stone and if you throw it in the river, then there is a certain, the whole river from Varanasi to Uttarakhand doesn't get disturbed. I mean, in quantum mechanics it gets disturbed, but in it only small part thing. So when the electron falls on the sample, there is a certain part of the sample from which all these signals are generated, and these three signals are secondary electron, backscattered electron and X-rays. Okay. Now what we saw is that the secondary, let's worry about secondary electron only. So the secondary electrons have very less amount of energy. The definition, the classical definition is 50 electron volt, the maximum energy that they can have. So the electrons which are generated only near the surface can escape into a detector system. The electrons which are generated down this are basically they don't have enough energy or kinetic energy to escape the sample. They basically get conducted anyways, but they cannot go into the detector, which is placed in some, I will see the photo of the chamber. Okay. So now you tell me that if I have a sample like this and the secondary electron only which are generated from here are able to reach the sample, and if I have a sample like this, this is sample number 1, this is sample number 2, and the beam again falls on this whole part. So now this area is, the whole area is the interaction area. In which case will more secondary electron reach detector, in case number 1 or in case number 2? Case number 2. Is there anybody who has any other opinion? Of course case number 2, because all these secondary electron which are generated from, if I take the same volume and if I make that volume like this, then all the secondary electrons only from here will be reaching the sample from the surface, but here this whole thing is surface. So the yield of secondary electron reaching the detector, the secondary yield of secondary electron which is reaching the detector, which in very complicated world is called coefficient of secondary electron emission, but let us not worry about those terms. These are all the English terms. They have, this is not an English class. Okay. So if I use a detector, then which one will appear brighter if I only take the secondary electron for imaging? 2 will appear brighter or 1 will appear brighter? 2 will appear brighter. So suppose your eye is a detector, system, and if I am standing here and if I keep switching off the lights which are over my head, I will appear dark. Okay. If I put on the light, I will appear bright. Has my color changed? No, only the light has been switched on, switched off, switched on. So, if your eye is detector, then the more photons which strike me and reach your eye, I look brighter, simple as that. So, if you take an electron detector and you place it somewhere, then this feature will use secondary electron, give out secondary electron more than this feature. So, this will appear brighter and this will appear darker. Can you see that correlation here? I am using a secondary electron detector to detect, and all these raised parts are giving away, are raised part are giving away more secondary electron. So, they all appear brighter, and all these flat parts, they appear dull. I will switch off that light. All these flat parts will appear dull. And if you see this image, then where do you think is the detector? Here, because this part of the image is nearly more brighter than this part of the image. Okay. So, by using a secondary electron imaging, you can image the topography of a sample. This is called topography. So, this is a flat topography, this is a rough topography. Similarly, in the last slide which I showed you, all these images basically are combinations of these rust are basically having, they are not smooth surfaces, they have all kind of elevations, cones and deformities. So, they all appear brighter, this flat metal part appears dull. Okay, this is just the amount of secondary electrons, coefficient of secondary electron, or how much secondary electron can reach the detector. Okay. Now, what else the, so this is one part of the inelastic scattering. What is the other signal which is produced by inelastic scattering? Sorry, the X-rays. And X-rays we will have tomorrow, we will have a session on spectroscopy, that we will talk in detail, but X-ray is basically used for chemistry or quantitative or qualitative, and basically chemical identification of the sample, because you will know that if it is an carbon atom or is a cobalt or copper or nickel and so on, they will give out their characteristic X-rays. Now, this is one thing. Now, there is one more interaction we studied. What was the other interaction? Backscattered electron. Now, this is a backscattered image of the same region of the sample, and this is the secondary electron image of the same region of the sample. Okay. Now, here there is nickel particles in Al2O3, and all these nickel particles are appearing bright, okay, and these are no contrast here. Okay. So, the backscattered, so the secondary electron is used for topographical imaging. The backscattered electron can be used for imaging of the different phases in terms of difference in chemistry, and we will see how. Let us just raise the screen again. Can you raise the screen again? You have to, can you help me raise the screen again? In the tea time we can get a battery on this. This battery is also very small, I do not know if they will get it. but if you have understood till now, you are way ahead in the understanding. Okay, so be happy about it. Not it is something that the imaging principle is very important to understand. There are a lot of complicated things happening because electron specimen interactions are not very easy. But I mean, how much can you do in? It takes almost the whole lifetime to understand electron microscopy. But yeah, that's why I told you this: relax and have fun. There is no need. Don't pressurize your mind to understand it. If in between you are lost in some thought, be in that thought and come. Don't worry. Yeah.
As you stated that if there is more images, there will be more secondary electrons.
Yes.
But in the second image, the secondary electron image has very less brighter. It also the image has more inches. Al2O3 and it has more rough surface. So it must need to show a brighter spot. Instead of showing brighter, why it is showing
Because I'll tell you why. So it is a good question. So I have to first rub the board. Second image, which is basically is not it still it is, you can see in the second image that the image was like this, and there was some Al2O3 and there was some nickel, right? But the overall there was not much of a very rough elevation and all. They were all nearly the same elevation. We will come back to that image. Let me first talk about the BSc, backscattered electron. Now we have used the secondary electron, and in a very classic, in a very ideal conditions, we have shown that it will produce contrast in this image 2, and it will not produce contrast or much rougher contrast, lesser contrast in image 1. So if this was imaged using secondary electron, you will see a nearly blank image. Okay, but if this was imaged using a secondary electron, you will see a topography, okay, which we saw in the last time. Now backscattered electron. So suppose that I take a sample, and in this sample there are two elements present, and let us call it is Z1 and Z2 are their atomic numbers, such that Z1 is very greater than Z2. Okay, two things which are very heavily apart in the periodic, tungsten or nickel, for example. Now if I take 100 electron, suppose, and I put on this part of the sample, and I told you that the backscattered electron are generated when the incoming electron comes, it interacts with the charge on the nucleus, it turns and it goes out. Not all of them go out, some of them will also inelastically scatter. There is a random event. Okay, it can be modeled using some modeling tools, but let us not worry about it. And suppose that this Z1 turns 80 electron out, and 20 of them get into the sample, and then they get into some interactions. Okay. If the same 100 electron now that falls on Z2 and remember Z1 is very greater than Z2, then the number of electrons that will be turned back will be less than the Z1, just because of the fact that the charge on the nucleus is lesser. So the number of, so there will be, because these electrons are coming at a very high velocity, so they have more tendency to get lost in the sample or get into the sample and cause other kind of interactions. So the number of electrons that will be turned will be, let us say, 50, and this 50 electrons will be basically gone into the sample to create other interactions. So now if I use a detector, okay, and I use a detector and I keep the detector here, then which part of the sample will appear brighter? Z1 will appear brighter because the more backscattered electrons are being detected from Z1, and this is a specific detector which is called a backscatter detector. Okay. Now, what is actually happening is that the backscattered electrons go much deeper and come out from the much deeper into the sample. So, the topography information is very poor because the energy of the backscattered electron is very higher than the secondary electron. So, the effect of topography is not important for backscattered electron. So, here the backscattered electrons which are from here and all over this sample will also be going to the detector. So, if you are using the backscattered electron for imaging, this will appear nearly similar to this. There will be a difference, but it will not be as sharp a difference as you get from the secondary electron, just because of the fact that the secondary electrons have very less amount of energy. So by using a backscattered electrons, we can make a difference between the chemistry, but we cannot make much difference about the topography. Using a secondary electron, we can make a large difference in the topography, but not much difference or nearly negligible difference in the chemistry. Okay. So now what happens is I will tell you the interesting geometry. So in the SEM, so you have to keep switching back and forth. You will see this SEM in the afternoon. So I have to important to show you that. Can you? We have to find a battery for this thing. Otherwise, I will have to ask him to always climb up and climb down. We will also have break in 5 minutes. Doesn't matter. And SEM is, okay, that you will see in the afternoon. This is what an SEM looks like. Most of you have already seen an SEM. Okay. So this, now I will tell you where things are, what we talked about. This is the gun part. Okay. This is the gun part, which is basically here. This is the gun, this is the negative potential, this is the positive potential. It is still moving. This is the negative potential, this is the positive potential, this is the first crossover. These are the condenser lenses. This is the image of the crossover, which is demagnified image. This is the image of this crossover, which is, this is the demagnified image of this, and this is a final lens, which is again demagnifying this to over the specimen. That don't worry about this, it is converging over the specimen. Okay. And these two are called condenser lenses, and this is also condensing the beam, but it is called objective lens. Any lens which is nearest to the sample is called the nearest to the object is the objective lens. Okay. So the thing which is nearest to the object is the objective lens. If you go and stand near to the object, you will also be called an objective person. So the so condenser lens, but it is also called the objective lens because there is a specimen next to it. And all these lenses will converge the beam here, that will create a signal, which these signals are 3 kinds. The interaction is 2 kinds, one is elastic interaction, other is inelastic interaction. The signal is 3 signals we have talked about: X-rays, secondary electron and backscatter electron, and these are basically coming to the detector system and getting projected on the computer. This is the computer. So what happens is that right here beneath the column, the backscattered electrons detector is there, and right here at an angle, you see this, This is a secondary electron detector. Okay. Now, the trick is very simple. The secondary electrons which are coming out of the sample. So, see my hand. So, this is a secondary electron detector. The secondary electron which is coming out of the sample basically has very less amount of energy. So, only the surface secondary electrons are able to escape the sample. So, the secondary electron detector which is in the side has a positive bias on it. So, these electron will go towards the detector and gets detected. They are so less energy that they will wander into the sample. So, it is having a positive bias. Okay. And the backscattered electron detector which is on the top. So, this detector has a positive bias. This is a backscattered electron which has a negative bias. It has a negative bias. So, will it catch the secondary electron? No. Secondary electron are anyways having very less amount of energy, and why would they go towards something which is again negatively charged? So, the backscattered electrons, so the secondary electron will all go in the secondary electron detector system because of the positive bias. The backscattered electron will basically can go into the secondary electron also detector also. Okay, but but if you have a negative bias, then they are coming out. It is assumed that they are coming out like perpendicular to the sample. So, they go at a high velocity into the backscatter detector system which is somewhere installed here. Okay. An X-ray system is installed. This is the X-ray detector which we will talk tomorrow, not today. Okay. So, now more or less you understand what an SEM is, I think, and what the imaging principle is, what are the interactions and what are the imaging principles.
It is shown bigger in the image also.
Yes, so it has a deflection coil system. So, what happens is that the image is coming down, okay, and the electron is coming down the column, and then it has a deflection system. So, basically it just deflects the beam to scan. So, that is the reason why it looks little bit more bigger in the image, but that is
Bias in different detectors, right? So does that bias doesn't result into some distortion?
it leads to distortion. We will talk about it in the next part. What we have shown till now is the world is perfect, but what we will do in the second half is that to show that how many imperfections are there and how to understand or deal with those imperfections. If I start with imperfections, then I will not have the audience in the next round.
Art stage kind of thing.
Sorry?
Art stage in near objective.
Yes, you can keep. The distance between the objective lens and the sample, they will show you that you can tell the computer that okay, now you shut down the backscatter detector, you only give me the secondary electron image, or you shut down the secondary electron detector, you give me the backscattered image.
So the normal SEM image will be considered.
No, at one time you can only switch on one detector. See, again I will show you. Suppose I am a secondary electron, okay, and there is a detector there, and I am very less energy. This is the backscatter detector. Okay, I do not have this is a negative potential, so I will drift towards the positive biased secondary electron detector. So, if I switch on the secondary electron detector and switch this off, basically I cut this, I just take a switch and switch it off, and I do not worry about the electron being lost in the chamber. But if I am a backscatter detector, I am having too much energy when I am coming out, okay, and it is assumed that geometrically that backscatter electron detector comes straight up the sample. Then even though this thing has, and suppose that backscattered electron detector is off and only the secondary electron detector is on, but still your sample is still giving out both the electrons, correct. You cannot switch off you cannot tell the sample that, I mean atom, that please do not give out this and give out that. The only command that you have is on the detector. So what happens is that what actually, why it is kept in the angle secondary electron is a backscattered electron which is coming out straight up from the sample. They are so much high velocity towards up that the nice small bias which is there will not change their path. So only the weak secondary electron which has to drift somewhere will actually like come out like this and then drift towards the positive volt. But the backscattered electron will go into straight up and hit somewhere. You get the point? So the interaction, the image will be now to say that no, zero backscattered electron will drift there is not correct. There may be some 10% which may even combine with the secondary electron image, but more or less it is not. And when your secondary electron detector is off and your backscatter is on, which is having a positive bias, so your secondary electron basically have so less energy that why would they go to a positive bias? They will just get lost in the sample. All right. So you think about the question, have tea, think about the question. We will discuss more questions in the afternoon, in the next session, 11th. Which are important, and let us discuss those terms. One is called the astigmatism, okay. And these are, see, whatever I speak is relevant to the usage of the machine, okay. I do not want to go too much into the theory aspect because that is a lot of books, but you will be doing practical in the afternoon, so you have to know those terms. So something is called an astigmatism. Now what is an astigmatism? Now many of us who wear glasses, when we go for checking of our eyes, you check for astigmatism also, okay. So the astigmatism is something when the current in the lens is not balanced, then you tend to get an image which is distorted, okay. So for example, if I draw a circle, if I draw a circle, okay, if you have astigmatism in your eyes, in your lens, in your retina, you will not see this as a circle, you will see this as an oval, okay. So you will see it as an oval, okay. So that is astigmatism. So if you it is better to get your eyes checked, because if you have astigmatism and you do not know about it, all your life you will be seeing a circle and oval. So what happens is that when in the electron microscope, if you draw the electron microscope here, can we raise this thing? I am sorry, I keep bothering you, but are there, I will give them to Praveen and he will pass it on. So you can use those slides later. Whatever I talk is written in the slide also. Okay. So now if you come to this schematic of the microscope that we build at the start, okay, if the current, if the lenses, both the side of the electromagnetic lens, if the current is not same, Okay. Then the this crossover and this crossover, this is the object, this is the image, and if the current is not balanced here, then this crossover will have an astigmatism. Okay. And what is going to happen is that the beam, instead of being a nice circle, will look like an oval. But what is interesting is that there is an under focus over focus condition. You may have heard about it. So if two beams are basically, if this is an convex lens and if this is a focal point, and what this is the optic axis, then this plane is under focus. So if you take the knob of the SEM and you do under focus over focus conditions. So basically what is under focus over focus? The final beam which is falling on the sample, you make this beam converge down once and then converge up once, instead of converging on exactly on the sample. So you basically change the current in the coil. So you are moving the beam up and down by changing the strength of the magnetic lenses, and then this will appear like this. It will just flip perpendicular. Then you know that there is an astigmatism. Okay. So if my if my eye has astigmatism, and if I go near this, it will turn like this. If I go far away from this, it will turn like this. So that is basically, so they will try to, so you can, when you are doing the practical, you can ask that person who is doing the practical that can you show me an astigmatic image, and then go under focus over focus condition. You can write it down, get an astigmatic image and do under focus and over focus condition to see that the image turns 90 degree or whatever you are seeing. Okay. So it is important that whenever you are using the microscope, you always go under focus over focus condition, and if it is not astigmatic, then it will go blurry and sharp. It will go blurry, sharp, blurry, that thing. Okay. So that is something that is, so astigmatism is one aberration. Okay. What is the second? What are the kind of lens aberrations you can have? Suppose in optical lens, what kind of aberrations you can have? You can have a chromatic aberration and a spherical aberration. What is a chromatic aberration? When you have a mixture of wavelengths, then those wavelengths will converge at different points on the optic axis, and that will give you a disc of confusion. Okay. So it simply looks like this. So if you have a lens, and if there is one wavelength, and this wavelength will converge here, okay, and if there is another wavelength and this wavelength basically will, let us say, converge here, then if you extend this and you extend this, then this is basically the disc of confusion. So that will cause an aberration. So in electron microscope, what we are using? We are using an electron, and therefore the electron, this power supply which is accelerating the electron at a very high voltage, okay, that power supply, if it is not stable, then you will have electrons coming down the column with different energies, and that could lead to different velocities, different forces, and therefore there will be aberrations in the system. And so the power supply in the SEM, which is typically used, this power supply is highly stable. So there is a huge amount of money that is spent in making this power supply very stable. So that now these things are something which the company always does. So you don't really have to, as a user, but you should know. The second is again this is chromatic, and then this spherical aberration, it has to do with if the lens is not perfectly spherical, if it has distortions, then it will lead to different amount of bending of the rays. There will also be a disk of confusion. So the lens's current and lens shape and size etc. should be very, very uniform. Okay, so astigmatism and aberrations, that is something that is important to know. Now, have you heard about double slit experiment? Okay. So, now double slit experiment everybody has heard. We will that using the double slit experiment we can define the resolution limit of a microscope. Okay. But we will not worry about it now. If you have heard about it, that is fine. But what one aspect of double slit experiment is that if you have a slit which is open, okay, and if you let a wave pass through it, okay, then you get a wave pattern on the other side, okay, and this distance, which is basically is more if this distance is less. This is inversely proportional. Okay, you know this thing. So, if I make a paper and I make a hole with this pen which has a thick point, the wave pattern there, and if I take a pin and make it small, the wave pattern will be differently broadened, because simply you can understand is that the diffraction that happens from the edges is different. Okay, we will mix everything together. So, keep these words in your mind. The third thing is depth of focus. Depth of focus is a very important term. What does depth of focus mean? That how much can you move an object in front of a lens while keeping the image at the same sharpness. Have you ever used a camera and realized that if you are taking a picture of somebody, the picture of the person who is behind is blurry, right? Background is blurry. So, you go for costlier and costlier cameras, and what those costlier cameras do is that they make better and better lenses to have a better depth of focus. Okay. So, that if I take his image, the image beyond that is also sharp and that is also sharp. Okay. Now, do you know that which camera in the world has the greatest depth of focus? Sorry? Who said I? Yes. So, our eye has the greatest depth of focus. So, by standing here, I can actually see this computer, him, 1 kilometer away, like half not away, maybe the building there at the same sharpness. So, our eye has a largest depth of focus. So, the nature has creates a camera which not even the Elon Musk can create, putting all his wealth. Okay. So, the question now is how do we combine? Now, let us see this thing. Now, there is one more concept. One more concept is this, that have you seen this kind of images that it is converging to a point? Okay. But what happens that when you are dealing with electrons, you are also dealing with particles. So, electron never converge to a point, they converge over an area. Okay. So, if I put electrons there, they will converge over a, so that is why we call this crossover. So, this is 50 micron and this is a certain size of the crossover. Okay. Great. Now, if this beam is falling over this area, suppose this beam, this I am just magnifying and it is coming over this dia, Then if you make a cylinder with dia d by 2 and d by 2 and this as d, okay, d by 2, d by 2 and this I make a cylinder. So, if I take the dia of the beam and make a cylinder with height d by 2, d by 2 and d, in that cylinder the focus is conserved. Okay. So, if you move in that cylinder anywhere, the focus will be same. Okay. So, if I make a bigger beam, will I have a higher depth of focus? Remember, the object is the sample and we are making an image of that sample. Okay. So, if I make the beam bigger, then the cylinder will also be taller. If the cylinder is taller, then the topography imaging will be easier because different parts of the topography will be in the same focus. Do you get the point? Okay. So, if I am, so if this is the topography and if my beam is larger, okay, then this cylinder is also larger because if this is d and this is d by 2 and d by 2, then in this, so I can actually image this at the same time at the same focus. So, it is easier to image a topography. Okay. Okay. Now, let us bring these things together. The more you in any microscope, optical microscope or electron microscope, the more you go away from the optic axis, the more distortion you produce in the beam. That is, if you see all the math that is there, all the math says the same thing. Okay. So, if this is the optic axis, if you define in this, if you define an optic axis, let us just if you define an optic axis which is this, right in the middle, the more you go away from this optic axis and you use those electrons, the more distortion, astigmatism, chromatic aberration and spherical aberration, they all come into picture. So, the easiest is to stay right middle of the optic axis. Use only those electrons which are coming in the middle of the optic axis. So, suppose that this is the optic axis, okay, and I am an electron and you are also the electron and you are also all coming and hitting this board which is the sample, then only if I use the optic, if I use this row and me electrons, then only I automatically get rid of most of the aberrations. Now, how can I stop those people and those people also hitting the board? By putting a wall, I bring a makeshift board and put it here, and I bring a makeshift board and put it here, and then I tell everybody to run towards the board. The only people who are not hidden by the makeshift board will actually reach the board, right. So, that two walls are called apertures. Okay. So, in the microscope we use apertures, you will hear this word objective aperture, condenser aperture. We use the aperture to cut down all the electrons which are away from the optic axis. Okay. So, let us just draw that thing. Where is the duster? Here. So, suppose that suppose that these electrons are coming down, and I am talking about this part of the whole machine, where the electrons have left this crossover and they are coming down and hitting the sample. So, we are here now, coming down, and I choose an aperture. It is like a physical plate with holes, okay, and I only use these electrons to come down the optic axis, okay. Then I give two conditions. One condition is this and other condition is this. I use an aperture which is a smaller size and I use an aperture which is a larger size. And if I now form an image of the beam over the sample, okay, and let that be shown as a cylinder, okay, because we are looking at the elevation, okay. Will this cylinder be big or will this cylinder be big? Can you tell me whether this cylinder depth will be higher or this cylinder, let us not wait, whether this dia will be higher or this dia will be higher? Let us call it 1 and this call is 2. And when we are talking about dimensions, we are all talking about micron size dimension, very, very small, or maybe I told you initially that if you take a paper in the single slit experiment, if I take, if the slit size decreases, the diffraction size, the wave size, the central beam, the central intensity wave size increases. So, if I keep decreasing this, I keep increasing the wave size. So, if I keep using smaller and smaller aperture, okay, I make the beam bigger and bigger. If I use bigger aperture, then the beam is smaller. It is the inverse, do not get confused. It is because, remember, now we are invoking the wave property of the electron. So, now you tell me that if you want to have a greater depth of focus, will you use a bigger aperture or will you use a smaller aperture? Smaller aperture, very good. If you want to have a bigger depth of focus, you will use a smaller aperture, and by using smaller aperture, you are also cutting the electrons which are away from the optic axis. So, you are getting better, you know, most of the aberrations you are removing. So, now there are this big mathematical equations about aberration, but I will tell you the thumb rule is you stick to the optic axis, you get better beam. You go away from the optic axis, the beam quality deteriorates, all kind of aberrations come in. Good. So, now if your friend tells, now let us take this case. So, you have used a smaller aperture, you get a bigger beam, you get a bigger cylinder, okay, and hence you get a better depth of focus. You use this, you get a smaller beam, you have a smaller depth of focus, okay, all right. Now, do you have any other tool in your hand? So, if you come here, do you have any other tool in your hand to actually reduce the size of this beam which is falling on the sample? Distance, very good, that is called working distance. Remember, we use this, what is demagnification? Image object distance by image distance. So, if we keep, so we are putting this beam here. Now, if we make this sample go down and up, then we can make this beam size also change, and keeping the aperture fixed. Okay. So, if we bring the sample down, will it change the demagnification, or increase the demagnification, or decrease the demagnification? What is the object here? In SEM, the object is always the beam and image is also the beam. So, image is this is the image and this is the object. So, if we keep the object distance same, we are not playing around with the condenser system. If we bring this sample down, then we are increasing the image distance, and demagnification is object distance by image distance. So, if you are increasing the image distance, you can make the beam smaller. Now, do not get confused, okay? Do not get too much tensed about it. What I am trying to tell you is that the beam size that falls on the sample is user controlled, okay, very much user controlled, and the beam size determines your depth of focus. So, if somebody gives you a sample which has lot of topography, like cracked sample, which has lot of topography, then you will use a larger size beam because it has a greater depth of focus. The cylinder height is also higher. If somebody gives you nanoparticles, or if somebody gives you nanowires or thin films, cross section, where the depth of field is not very big an issue. Nanoparticle, how much depth of field do you need? It may be 50 nanometer particle or 100 nanometer particle. You really do not need a cylinder of 1 micron focus conserved cylinder. Then you can make the beam smaller. How can you make the beam smaller? You can increase the aperture and make the sample go closer to the lens. Now, I tell you that okay, I want to image nanoparticle with a beam which has least aberration. So, you are working in a company and I tell you that okay, you get me an image condition where you give me a less aberrated beam with which I can use for imaging nanoparticle. So, how can you first is that how can you remove the electrons which are away from the optic axis? By using smaller aperture. So, you use a smaller aperture and then you decrease the distance. So, you have a less aberrated beam with a smaller spot size. If you can write down this word, that if the aperture size and the working distance determines the size of the beam over the sample. And one more thing which is quite obvious, which you may not have realized, that this beam size which you are actually using as an object also depends on this condenser lens strength also, no. What we are doing is that the first crossover we are decreasing again and again. So, and we are now talking about these two beams. So, object itself, if we keep reducing, then we also reducing this. So, more you reduce this, the more you get a smaller and smaller beam. Now, the question is why do we need a small beam on the sample? Now, you understood about the depth of focus. See, larger beam, greater cylinder, better depth of focus, different parts of the sample which are of different topography all at the focus at the same time. If you do not need that, you are imaging nanoparticle, you can make the beam small. Now, the question is, why do we need a small beam? Because in SEM, remember, the imaging happens in that the spot by spot. So, it hits there, it generates signal, it hits there, it generates signal, it hits there, it generates signals. So, if you make the beam larger, then you are convoluting the information. So, if I can draw it, you hit the sample here, it generates this thing. If you hit the sample here, it generates this interaction with where the signal comes from. So, say SE comes from, BSC comes from, and it does this thing raster. So, it rasters like this, it rasters like this. Now, the smaller the beam, the more number of points you can actually put the beam on, and that would increase the information resolution. Do you get the point? Which can increase the information resolution. So, you need a smaller and smaller beam. And how can I go to smaller and smaller beam? I can remove the aperture completely. Completely removing the aperture is the largest aperture and make the sample go towards the lens. But does that give you some breaks? Of course, it gives you break, because if you remove all the aperture, you are using all the aberrations, and you cannot take a sample and you cannot physically hit the lens. So, you are limited by the distance, and you are limited by the aberrations in the. So, if you bring down the aberrations in the beam by using a stable power supply, a nice balanced current in the lens, then you can actually be relaxed from that front, okay, and you can play with the sample height. But you are using a bad quality microscope, your lenses are also, the power supply is also, the bulb is like doing this, and you are running SEM in the same voltage, then it is no hope, right. So, now the question is this: suppose I get a very ideal conditions, okay, and so there is a limit to which I can shrink the size of the beam, okay, and that produces a challenge in the amount of information resolution that you can get from a scanning electron microscope. So, if somebody says that I want to image 50 nanometer particle, 100 nanometer particle, that is fine. Nowadays SEM can do that, but if you say that I want to image a feature which is atomic column or a 2 nanometer size, that is not possible in the SEM. Okay. So, that one has to also understand. Okay. Now, good. So, let me ask you one question. So, if suppose that I have a large topography, some friend of yours gives you a large topography sample. We have some 15-20 minutes, we will do some exercise here. If you have understood till now, we have done good, okay. So, suppose if your friend gives you a large topography sample, very large topography, I mean it is like a cracked sample. In metallurgists, they break things. So, they break metal wires and then they see in the SEM, okay. And you say that okay, fine, I know that I have to use a bigger beam, because the bigger beam has a larger cylinder. So, bigger topography will all be in the focus at the same time. So, what you will do is that you will use a smallest aperture, okay, and you will use a very small aperture, and you are happy that okay fine, I am also now able to cut the beam which are away from the optic axis, and you will move the sample down, down, down. Okay. So, if this is the SEM chamber, you will move the sample here and you use the lowest aperture, and then you say that now I have the biggest beam in the world. So, the biggest cylinder height. So, now do you think, can you think that is there may be a limitation there also? Sorry?
If you increase the distance between object, lens and object, downside sample, there will be distortion create, no?
No, not distortion. I'll tell you because it is difficult to imagine. The problem is now the camera. So, I'll fine. We'll come to all this thing, but now the problem is the camera. Okay. Now, how does the camera operate? Camera operates on a pixel basis, right? So, if you take a mobile phone, then you go and buy it, and it tells you this is this many pixel by that many pixel. Okay. So, what happens in an SEM is that your sample is mapped to the camera. Okay. 1 second. So, this is your sample. Suppose this is a top view of your sample, and the electron is rastering like this, and it is and every time it hits the sample, it generates all the signals, which is the secondary electron, backscatter electron, and X-ray. Tomorrow we will worry about X-ray in my lecture. Tomorrow morning there will be a sample preparation lecture. Afternoon we will do X-ray. X-ray mean the X-ray for chemical analysis. Now, suppose that this is your camera, which is fixed in the machine. You ask them in the afternoon, they will show you the camera. And suppose this camera is m pixel by n pixel. Okay. Just let us pick a number 1000 by 1000. So, this has a grid which is 1000 by 1000. Now, if you tell, if in SEM, if you are scanning your sample, the total sample you are scanning in the SEM, and most of you have done SEM, then the computer, it takes this 1000 by 1000 and maps here. So, now this whole sample is divided into 1000 pixel by 1000 pixel, and the raster now happens accordingly. So, the beam now goes 1000 times this way and 1000 times this way, and the information, and every time the intensity, number of electrons is the intensity in the detector, and that intensity is plotted in the camera here. So, if some things gives a higher secondary electron, that is plotted bright, and somewhere it does not get highest 0, then it dull, and somewhere it is get the coefficient is not 1, it is 0.5, that is little grey, and that is how you create an image. Now, when you hit magnification, you hit plus, right? You hit magnification. You say you turn a knob, magnify. Then what, when you hit magnification, when you magnify, what actually happens is that the beam now rasters over a smaller region. The beam now rasters over a smaller region, and now this smaller region is represented in the same camera, because camera is a hardware. And this region is now converted into 1000 into 1000. Now, if this is converted into 1000 into 1000 and it is being projected in this thing, then will the same beam size be helpful, or you have to reduce the beam size now? You have to reduce the beam size, because if you keep the same large beam size, then that information is convoluted. Now, the beam is like this, then you are getting the interaction volumes are in overlapping. So, the image will get blurry and blurry. So, so a wise microscopist who does not exist, is a myth, but a wise microscopist, when every time that person increases the magnification button, he will change the beam size, and the beam size could be changed by several ways. Now you know I can use this condenser lens to change this beam size, and subsequent beam size will get changed. I can use this objective lens aperture to change the beam size. I can change the distance to change the beam size. In many ways we can change the beam size, okay, but nobody does it, okay, because a slot is only for 1 hour, and either you will get the data or you will do the circus. So it is good to get the data and get away and have tea than to do. So every time you change the mag, you same pixel is plotted here, and now again I increase the mag, for example, and then I make even the area even smaller, then the same 1000 by 1000 is now projected here in this smaller circle, in this smaller cube, 1000 by 1000. So I have to make the beam even smaller. Is there a limitation to making the beam smaller? Yes. You can, if you how can you make the beam smallest? By removing all the aperture and by making the sample go near the objective lens, pole piece. But then also electron has a area on which it will collide. So what happens is that if you keep increasing, somebody will say, keep increasing the magnification, we will see, but it also then you reach a physical barrier. If you remove all the aperture, all the aberrations pour in, they will make the beam distorted, okay. You cannot go and hit the pole piece, there is a distance limitation there also, and also the electron also has a particle nature, so it cannot converge to a point. So all these things will limit the amount of information that you can get from the SEM, okay. But in TM that is not the case, because in TM the imaging principle is very different. It has to do with the basically the phase contrast, but that let us not worry about it. So in scanning electron microscope you are limited by this thing. So the rule of thumb is this, that if you have a sample which has a large topography, then you use a larger beam, okay. You use a smaller aperture and larger working distance. If you have a sample which is nanoparticle, you do not need a high depth of focus, okay, then you use a larger aperture and a smaller working distance, okay. These are all in the slide. And all the SEM in the world, basically now the sample preparation will be talked about in the next, by tomorrow morning. All the SEM in the world, they are highly prized, and the reason why they are highly prized is because of two things. One thing is a very stable power supply, it has to be very stable, okay, and you will have to have a camera which is very high quality, and because this more the pixel this camera is, more better resolution you can get, okay. It is same as our phone camera. No, if this is a better camera, okay, and if I go nearer and nearer, I can get better details projected on the camera, okay. Is there any question? You can ask a question. We are already an hour into the. So let me quickly revise. Tomorrow again we will meet. So SEM is basically an electron microscope which uses electrons, okay. And the reason why we use SEM is that the electrons basically can interact with the sample and can produce a lot of signals, okay. Now the standard definition of resolution in optics is given by the Rayleigh's criteria. You know what is Rayleigh's criteria? Sorry? Not elastic set, I will tell you. It all starts with the double slit experiment. Okay. If you have a wave which is passing through this, okay, they will give you a wave pattern here from the slit 1. The slit 2 will also give you a respective wave pattern. Slit 2 will also give you a wave pattern, and that wave pattern basically will be somewhere here, similar to that. Okay. Now, if you keep moving this, if the maxima of the second one collides with the minima of other one, then the sum of the wave is this, the dotted line, and this is the distance which can be resolved. So, if you have two holes in a paper, okay, and you are using any kind of wave, be it electron wave or light wave, to image that thing on that wall, then the hole will not appear as a hole, it will appear as a wave pattern. So, all the holes in the paper which you can see by eyes, of course, but if you are using a wave, will appear as a combination of waves. So, this slit will appear as a combination of wave, this slit will appear as a combination of wave, and if the minima and if the minima of this and the maxima of this collide, such that this is the summation wave which is in the dotted line, then this, so from that dip you can perceive that there are actually two slits present, and this distance in conventional optics is called resolution limit, and that resolution limit is basically is a function of lambda by mu sin alpha. Okay. Mu is the refractive index of the medium between the this is the refractive index of this medium, and sin alpha is the convergence angle. So, this is the lens, this is the sample, and lambda is the wavelength. So, smaller the wavelength, the better will be the smaller will be the d, the better will be the resolution. Do not worry about understanding it. Okay. Just listen to me. I do not think that these things you can get in 5 minutes. Sometimes you have to take things on face value and understand it later. So, just take it on face value. So, the smaller the wavelength, the better, the smaller is the d and better is the resolution. So, all the electron microscope, especially transmission electron microscope, where the sample passes through the electron passes through the sample, and what is the sample made up of? It is made up of these channels of atoms, and all these channels of atoms are basically the slits, and these channels of, you are physicists most of you. So, all these channels of atoms, how far apart they are? Couple of angstroms. So, if they are couple of angstrom apart, then to have this d measurable, this d is very small, and therefore, you need alpha which is very small to have that resolution. And how can you make wavelength smaller and smaller? By high energy, and the electron, any electron can be accelerated. Why? Because it has a charge, and if you use a potential, you can accelerate the electron to very high velocities to have wavelengths which are nearly 0, very very small wavelength, and therefore you can beat the resolution limit. Okay, but that is when your electron is passing through the maze of the slits. But in SEM, you are not using that fundamental. SEM, you are having an interaction volume. So 5 minutes, this is important. You have interaction volume. Now I told you one more thing that is important, that if you are scanning like this and you want to scan more number of points, then you can do that by beam size is one thing. What else can you do to change the dia of this interaction? One is that beam size, which is this, but you want to make this interaction look like this. What can you do? Not scan rate. You keep this. You slow down. You bring the energy of the electrons down. So the amount of havoc they create inside the sample is less. So if I take a ball and I throw it on the wall at certain energy, it does damage to the wall. I throw the same ball at lesser energy, it will do smaller damage. So I can actually change, I can keep the beam size same, but if I reduce this positive potential, instead of using 20 kV, I use 10 kV, the electron is weaker in energy, right. So it will create a smaller interaction volume. So I can have better information resolution. Okay. So I can also play with the interaction volume. So how many? So you can bring down the beam size. You can also bring down the energy of the electrons when they hit the sample, and that by which if you are able to bring down the interaction volume, then you can have more number of tapping. Or if for the fixed number of tapping, which is maybe determined by the camera, the interaction volume, a smaller interaction volume will give you a better information resolution. If I have to, I know you are all tired, including me. If I have to tap here 5 times, 1, 2, 3, 4, 5, okay, and the amount of havoc that I create beneath it is such that those 5 volumes are completely separated from each other, then I get some information on the top screen. If I hit that thing now much harder, 5 times, okay, and those disturbances are now bigger and they are overlapping with each other, the information that is now projected is not good. It has convoluted information. You are thinking that this part of the sample has something, but actually the information is also coming from the next point, right. So if I bring down the energy, so if I know that okay, my camera has this much pixels and I map the sample with this many pixel, and I need to have that size of my interaction volume, then I can bring down the beam size. I can also bring down the energy of the electrons and have a very nice image. How many microscopists in the world do that? 0, because that is too much work. Okay. So what you actually do, we are living in a real world. For every magnification knob, you cannot change the kV, you will not change the beam condenser lens current, you will not move the sample up and down, or you will not remove the aperture. You know, it's like having one roti and then going and making the other one, and then having that one and making the third one and having, that is not going to happen. So what we do is that in the real world, the microscopists use a certain middle path numbers. So they will do, what they will do is that they will, and these middle path numbers I will tell you, they will keep this thing as 20 kV, the working distance they will keep as 10, and aperture they will keep some middle aperture. So, if there are 5 aperture sizes, they will say that okay, we'll keep this middle aperture or whatever that aperture dimension be, and then they will do magnification, different magnification imaging at that condition. So, that is I mean that is okay, when that is a real world, we have to live with that. Fine. So, we will stop here. I think this is lunch time. Tomorrow morning Professor Surendra will talk about sample making, and again after tea tomorrow we will talk about, now we have only used the electron for imaging, we will now use the electron tomorrow for chemical analysis, which is spectroscopy. Okay, fine, all right, we will meet tomorrow. If you have any, one group will be doing a normal SEM, other group will be doing the sample preparation using FIB. Tomorrow the groups will switch. Okay, that you do you know where is, I think Praveen will make arrangement to take you there to the center. Okay, thank you.